Right now, somewhere in the cold dark between Jupiter and the Sun, a spacecraft the size of a basketball court is drifting through space at roughly 75,000 miles per hour. It was built by thousands of people across 2 decades. It carries instruments so sensitive they can detect a single molecule in a cloud of gas. And it is heading toward a moon that most people have never thought about, a small, frozen, cracked world orbiting the largest planet in our solar system, a world that may be the most important place in the entire solar system for one reason and one reason only. It may not be dead. Right now, beneath a shell of ice so thick it would take a drilling machine decades to penetrate, there is an ocean, not a lake, not a thin film of slush, an ocean, liquid water in quantities so vast they make every drop of water on Earth look like a puddle left after a summer rain. This ocean has been sitting there in complete and total darkness for approximately 4.5 billion years. No sunlight has ever touched it. No wind has ever crossed its surface. No shore exists along its edge. It wraps the entire moon in a single connected body of water, sealed above by ice and held below by a rocky seafloor that no human eye has ever seen and that no instrument has ever directly measured. For decades, scientists knew the ocean was probably there. The math pointed to it, the magnetic readings suggested it. But knowing a thing is probably there and confirming what is actually inside it are 2 entirely different problems. The ocean of Europa was the solar system's most tantalizing locked box. We could hear something moving inside it. We could not open the lid. Then James Webb turned its mirrors toward Europa for the first time. What came back changed the conversation permanently, not because Webb found life. It did not. What Webb found was something in certain ways more unsettling than a simple yes or no answer. It found chemistry that should not be there. It found carbon rising from the deep in a pattern too deliberate to be random. It found salt concentrated in exactly the places where the ice looked most recently broken. It found a moon that, in the language of planetary science, is leaking. And the word leaking means the sealed lid is not perfectly sealed. The interior and the exterior are talking to each other. Something below is pushing up, and what is below is an ocean larger than all of Earth's seas combined, sitting in darkness, running on chemistry that on our own planet has only ever been associated with one thing: life. We do not know if Europa has life. That sentence needs to be said plainly and held clearly throughout everything that follows. The data does not prove biology, but the data also does not look the way a dead world is supposed to look. And the gap between those 2 statements is where the most important scientific story of the coming decade is unfolding. If discoveries like this one make you stop and reconsider the size of the universe and your place inside it, take a moment right now and hit that like button and subscribe. It genuinely helps this channel continue doing exactly this kind of work. Every subscription is a small signal that says this kind of careful, unhurried exploration of what we actually know about the cosmos is worth making. Get comfortable, we're going a long way tonight. Let's begin. To understand why Webb's findings matter, you first have to understand what Europa actually is, because most people who have heard the name have a vague impression of a frozen moon somewhere out beyond Mars. And that impression, while technically accurate, misses almost everything important about the place. Europa is the 4th largest of Jupiter's many moons. It is slightly smaller than our own moon. If you placed it next to Earth, it would look like a marble sitting next to a basketball. From a distance, it appears almost perfectly smooth and brilliantly white, more reflective than almost any other solid object in the solar system. The surface is bright because it is covered in water ice, fresh, clean, constantly resurfaced ice that reflects sunlight back into space with extraordinary efficiency. Up close, the smoothness disappears entirely. The surface of Europa is covered in lines, thousands of them, long, sweeping cracks and ridges that run for hundreds of miles in parallel pairs, crossing each other at angles, curving gently over the horizon. Between the lines, in certain regions, the ice has been shattered and rearranged into chaotic jumbles that look from orbit like a jigsaw puzzle assembled by someone who did not care whether the pieces fit. The surface has no large craters. This is one of the most important facts about Europa. A world that has been around for 4.5 billion years and has almost no craters is a world that keeps erasing its own history. The surface is young. Something keeps renewing it. That something is what this story is about. To picture Europa's place in the solar system, stand in your imagination somewhere in the American Midwest and face west on a clear night. The nearest bright object in the sky after the moon is likely Venus or Jupiter, depending on the season. Jupiter, when it is visible, looks like a very bright star, slightly cream-colored. It is roughly 400 million miles from Earth on average. Europa orbits Jupiter at a distance of about 417,000 miles from the planet's center. That means Europa, at its closest to Earth, is still roughly 390 million miles away. The light you see when you look at Jupiter left that system more than half an hour ago before it reached your eyes. That is where we are sending our instruments. That is how far away the answer might be. Now, let us talk about the ice. The shell of ice covering Europa is estimated to be somewhere between 3 and 30 miles thick, depending on where you measure it and which model you believe. This enormous uncertainty is not a failure of science. It reflects the genuine difficulty of measuring the interior of a moon from a distance using only indirect methods. The best current estimate, derived from observations by the Juno spacecraft in 2022 and 2024 and published by a team led by Stephen Levin at NASA's Jet Propulsion Laboratory in late 2025, puts the average thickness at roughly 18 miles, with an uncertainty of about 6 miles in either direction. 18 miles of ice. To make that concrete, consider this. The deepest humans have ever drilled into Earth's crust is a borehole in Russia called the Kola Super Deep Borehole, which reached approximately 7.5 miles down after more than 2 decades of continuous drilling under ideal conditions on a planet where humans live and can service equipment in person. Europa's ice is more than twice that depth, located nearly 400 million miles from the nearest repair facility, in an environment with radiation levels that would kill an unshielded human in under 20 minutes, at temperatures that hover around minus 280 degrees Fahrenheit. Reaching Europa's ocean through conventional drilling, with technology available today, is not merely difficult. It is not possible. This is the wall that has defined Europa science for the past 30 years. The ocean is almost certainly there. Reaching it directly is beyond our current engineering. And so the entire field of Europa research has been built around a different strategy. Instead of going through the wall, you read what the wall is exhaling, you stand outside and listen, you measure what leaks out, you analyze the stains on the surface, and work backward to what produced them. That strategy is what Webb was designed to advance. And to understand what Webb found, you first need to understand why Europa has a liquid ocean at all, because on its own, a moon that small that far from the sun should be completely frozen solid. The sun's warmth at Jupiter's distance is less than 4% as intense as it is at Earth. A world that small cannot hold internal heat from its formation for billions of years. By any simple calculation, Europa should be a dead frozen rock, indistinguishable from 1,000 other airless moons scattered across the outer solar system. It is not. And the reason it is not is one of the most elegant pieces of physics in our solar system. Jupiter is enormous, not just large. Enormous in a way that strains ordinary language. Jupiter contains more than twice the mass of every other planet in the solar system combined. Its gravitational field is not a gentle tug. It is a crushing force that reaches out across hundreds of millions of miles and reshapes everything near it. Europa, orbiting at 417,000 miles from Jupiter's center, sits deep inside that gravitational field. And Europa does not orbit in a perfect circle. It orbits in a slightly stretched oval, an ellipse. This means Europa's distance from Jupiter changes as it travels around its orbit, sometimes closer, sometimes farther. When it is closer, Jupiter's gravity pulls more strongly on the near side of the Moon than the far side, stretching Europa slightly into an oval shape. When Europa moves farther away, the stretching relaxes. The Moon flexes back toward a sphere. Then it gets pulled closer again and stretches again. This happens every 3.5 days, every single orbit, without pause, without rest, for the entire history of the solar system. Imagine taking a metal rod and bending it back and forth thousands of times. The metal heats up, not from flame, not from radiation, but from the mechanical energy of repeated flexing being converted into heat. Europa is that metal rod. Jupiter is the force bending it. And the heat generated by 4.5 billion years of continuous tidal flexing is what keeps Europa's deep interior warm enough to maintain an ocean of liquid water under all that ice. This mechanism is called tidal heating, and it is one of the most important concepts in planetary science because it means warmth, and therefore habitability does not require proximity to a star. Any moon caught in the right in here, gravitational relationship with a large enough planet can be kept warm from the inside out, indefinitely, for as long as its orbit remains stable. For Europa, the result is an ocean, but not just any ocean. An ocean 60 miles deep, on average. An ocean that wraps the entire moon with no shoreline, no continent, no surface access, sealed above by ice and contained below by a rocky seafloor. An ocean whose total volume is estimated at roughly 3 billion cubic miles of liquid water. Earth's oceans, the ones that cover 70% of our planet's surface and hold all its marine life, all its coral reefs, all its deepest trenches, contain approximately 340 million cubic miles of water. Europa has roughly 9 times more liquid water than Earth. Let that settle. The blue planet, the water world, the world we named after an ocean goddess, is outclassed in pure liquid water volume by a frozen moon half the size of our own. The solar system's largest body of liquid water is not here. It is out there, sealed under 18 miles of ice, orbiting a gas giant in the cold dark beyond the asteroid belt. And it has almost certainly been sitting there for 4 billion years, undisturbed, running whatever chemistry it runs, in complete and total isolation from the rest of the universe. The first strong scientific evidence for this ocean came not from a telescope, but from a spacecraft. Galileo, a NASA probe that orbited Jupiter from 1995 until 2003, performed 12 close flybys of Europa during its mission. On each pass, its magnetometer measured the magnetic field around the moon. What Galileo found was anomalous. Europa was generating a changing magnetic response, a fluctuating induced field that varied in sync with Jupiter's rotating magnetic environment. There is only one known mechanism that produces this kind of response in a small rocky moon. A layer of electrically conductive material in the interior being pushed back and forth by Jupiter's magnetic field like a wire moving through a magnet, generating a current, which in turn generates the magnetic response Galileo was measuring. The most electrically conductive material that could plausibly exist inside Europa at those temperatures is salty liquid water. Salt dissolved in water conducts electricity. Pure ice does not. Frozen rock does not. Only liquid water, with dissolved minerals, fits the profile of what Galileo detected. That reading did not prove an ocean, it strongly implied one. And over the following 2 decades, every additional piece of data, from improved magnetic models, from surface imaging, from the thermal properties of the ice shell, continued to point in the same direction. By the time James Webb turned its mirrors toward Europa in 2022, the scientific consensus was not really whether Europa had an ocean. It was about what was in the ocean and whether anything was alive down there. Those are the questions Webb was designed to begin answering. Not by looking through the ice. Webb cannot see through ice any more than your eyes can, but by reading the chemical fingerprints on the surface with an infrared precision no previous telescope had approached. Because whatever chemistry is happening in the deep ocean below is slowly, steadily, over geological time, being pressed upward through the cracks and chaos terrains and deposited on the surface above. The surface of Europa is a receipt. A very old, very complicated, partially radiation-damaged receipt from a transaction happening 60 miles below in a dark, salty sea. Webb's job was to read the receipt. And the first line on that receipt, the one that made the room go quiet when the data came in, was a single chemical in the wrong place. Before we follow that chemical down to its source, it is worth pausing on what Webb actually is, because the instrument's capabilities define what kind of reading is possible. The James Webb Space Telescope launched on December 25, 2021 and reached its operating position approximately 1 million miles from Earth in early 2022. It is the largest and most powerful space telescope ever built. Its primary mirror is made of 18 gold-coated hexagonal segments that together form a collecting area of approximately 270 square feet. Deployed in space, the full mirror assembly is roughly the size of a tennis court. It is designed to observe primarily in infrared light, wavelengths of light that human eyes cannot see, but that carry chemical information that visible light does not. Infrared light is essentially heat radiation. Every molecule vibrates. Different molecules vibrate at different specific frequencies. When infrared light passes through or bounces off a material, certain frequencies are absorbed by the molecules in that material. The pattern of absorbed frequencies is unique to each molecule, like a fingerprint. By measuring which frequencies are missing from the reflected light, you can identify exactly which molecules are present in a surface, even from enormous distances. With extraordinary precision, Webb's infrared sensitivity is approximately 100 times greater than the Hubble Space Telescopes in many wavelength ranges. To put that in the language of ordinary experience, if Webb were a human eye, it could detect the heat of a single candle flame on the surface of the Moon from Earth. For a moon nearly 400 million miles away, this sensitivity means Webb can detect trace amounts of specific chemicals that previous telescopes could only guess at. When Heidi Hammel of the Association of Universities for Research in Astronomy led the first solar system observations with Webb in 2022, Europa was on the target list. The observation window was short, only a few minutes of telescope time, in the crowded schedule of the most sought-after telescope in human history. A few minutes is all that could be allocated. The team did not expect dramatic results from such a brief look. They were hoping for confirmation of what Hubble had already hinted at, a general picture of the surface chemistry to establish a baseline. What they got instead was a detailed chemical map that exceeded what decades of previous observations had produced. The infrared fingerprints were sharp, the signal was clean, and within those fingerprints, one signature stood out immediately. It was sitting in the middle of the most geologically disturbed region on Europa's visible face. It was a molecule that should not have survived long enough to be detected, and its presence in that specific location told a story that no geological model at the time was fully prepared to explain. The molecule was carbon dioxide. The carbon dioxide Webb detected on Europa's surface was not a surprise in the way that finding a completely alien element would be a surprise. Carbon dioxide is common. It is in the air you are breathing right now. It forms when carbon and oxygen combine. It is produced by volcanoes, by chemical reactions between rock and water, by living organisms exhaling, by organic material decomposing. In the solar system, it shows up on Mars, on Venus, on comets, on asteroids. Finding it somewhere is not, by itself, remarkable. What was remarkable was where it was sitting on Europa, and what was remarkable was what it was sitting next to, and what was most remarkable of all was that it was there at all, because carbon dioxide on Europa's surface should not last. Jupiter's radiation environment is one of the most hostile in the solar system. Europa orbits inside Jupiter's magnetosphere, a vast region of charged particles trapped by the planet's enormous magnetic field and accelerated to near the speed of light. The radiation dose at Europa's surface is approximately 500 rem per day. For context, the total radiation dose that would kill a healthy human adult is around 500 rem. An unprotected astronaut standing on Europa's surface would absorb a lethal dose in roughly 24 hours. Within 20 minutes, they would already be experiencing the first symptoms of acute radiation syndrome. This radiation does not only destroy living things, it destroys molecules. Specifically, it bombards the surface ice with high-energy particles that knock chemical bonds apart, shatter complex molecules into simpler fragments, and scatter the pieces. Any molecule sitting exposed on Europa's surface is being continuously dismantled by Jupiter's radiation. The timescale for this destruction depends on the molecule, but for carbon dioxide, the math is unforgiving. In the radiation environment near Europa's surface, carbon dioxide should be broken down and dispersed within a few million years at most. In cosmic terms, a few million years is not a long time. Europa is 4.5 billion years old. Any carbon dioxide that formed on its surface in the distant past should have been radiation processed into other compounds long before humans appeared on Earth. The carbon dioxide Webb detected should not have been there. Not in those concentrations, not in that pattern, not unless something was continuously replacing it. That replacement is the signal. That is the receipt being handed to us from below. The team that analyzed Webb's Europa data was led by Geronimo Villanueva at NASA's Goddard Space Flight Center. Villanueva specializes in planetary atmospheres and surface chemistry, and his group has spent years developing the techniques needed to extract precise chemical information from Webb's infrared readings. When the Europa data arrived, they processed it alongside a second team led by both teams published their findings in the journal Science in September of 2023. The conclusion both teams reached was the same, and it was stated with a clarity that left little room for alternative interpretation. The carbon dioxide on Europa's surface did not come from space. It did not fall in on comets or drift in with interplanetary dust. It was not produced solely by radiation chemistry rearranging other molecules on the surface. The carbon came from inside Europa, from the ocean. It was pushed up through the ice relatively recently, deposited on the surface, and detected by Webb before Jupiter's radiation had time to finish destroying it. To understand how they reached this conclusion, you have to follow three separate lines of evidence, each one ruling out a different alternative explanation, and all three converging on the same answer. The first line is geographical. If carbon dioxide arrived from outside Europa, from comets or meteorite impacts, you would expect it to be distributed across the surface in a pattern that reflects the randomness of impact. Craters scatter their contents outward in all directions. Dust settles more or less uniformly across a surface over time. You would not expect to see carbon dioxide concentrated sharply in one specific region, while the rest of the surface shows little or none. Webb saw exactly that kind of sharp concentration. The carbon dioxide was overwhelmingly concentrated in a single region near Europa's equator called Terra Regio. Outside Terra Regio, the carbon dioxide signal dropped sharply. The pattern had a boundary. The pattern had a center. The pattern did not look like something that rained down from above. It looked like something that welled up from below. Terra Regio is what planetary scientists classify as chaos terrain. The name is not metaphorical. It is a technical descriptor for a specific kind of surface geology found on icy moons, and it refers to regions where the ice has been broken into irregular blocks, rotated and shifted relative to their neighbors, partially melted and refrozen in configurations that no longer match the surrounding surface. If you have ever seen a photograph of sea ice breaking up in spring, flows of different sizes jostling and tilting against each other with dark water showing between them, then you have a rough visual intuition for what chaos terrain looks like from orbit, except that in Europa's case, everything has since refrozen into a permanent record of the disruption. Chaos terrain forms when the ice shell is destabilized from below. Either the ocean rises locally and partially melts the underside of the ice, or warm material within the ice shell itself rises toward the surface and softens the upper layers. Either way, the surface above breaks apart. The pieces drift and rotate, and eventually the whole mess refreezes in its new disordered configuration. The resulting terrain is a geological record of a moment, or a series of moments, when the interior of the moon was pushing hard against its own lid. The fact that Webb's carbon dioxide was concentrated precisely over one of these chaos regions was not a coincidence. The chaos terrain is where the ocean and the surface have been in closest communication. The chaos terrain is where material from below has the shortest path to the surface. Webb was reading the chemistry of the ocean through the most porous, most recently disrupted section of the ice shell. The second line of evidence was chemical. If the carbon dioxide had been produced purely by radiation chemistry on the surface, rearranging other molecules already present, you would expect it to be uniformly distributed wherever those source molecules were present. Radiation falls on the entire surface. If it were generating carbon dioxide from local material, The distribution should be broad and relatively uniform, tied to the distribution of whatever precursor materials the radiation was processing. Webb did not see broad uniform distribution. It saw sharp concentration, and the concentration tracked the chaos terrain boundary with a precision that ruled out surface-level radiation processing as the primary source. The third and most technically sophisticated line of evidence came from isotope measurements. Carbon atoms come in two stable varieties. Carbon, 1,2, has 6 protons and 6 neutrons in its nucleus. Carbon, 1,3, has 6 protons and 7 neutrons. Both behave almost identically in chemical reactions, but not quite identically. Different processes produce slightly different ratios of the two varieties. Comets have a characteristic carbon isotope ratio. Interplanetary dust has a characteristic ratio. Material that has been processed by geological reactions deep inside a planetary body has a different characteristic ratio, and biological processes have yet another distinctive signature, one that preferentially selects the lighter carbon, 1,2. Webb measured the isotope ratio of the carbon dioxide at Tara Regio. The ratio was consistent with material that had undergone processing inside a planetary body, specifically the kind of chemical interaction between water and rock that occurs in a hydrothermal environment. It did not match the cometry ratio. It did not match the interplanetary dust ratio. It matched an internal source. Samantha Trumbo's published statement was measured but direct. She described finding observational evidence that the carbon on Europa's surface originated in the ocean as not a trivial thing. Carbon, she noted, is a biologically essential element. Confirming that Europa's ocean contains it changes the ocean's status from a body of water with unknown chemistry to a body of water with the foundational chemistry that life as we know it requires. Before Webb, the habitability case for Europa rested on 3 pillars: liquid water, confirmed by Galileo's magnetic readings; energy, provided continuously by Jupiter's tidal heating; and chemistry, which was the uncertain one. The water and the energy were reasonably well established. But a body of water with energy is not automatically a place where life can begin. You also need the raw materials. You need the molecular building blocks that biological processes can work with. Carbon is the most fundamental of those building blocks. Every known form of life on Earth is built around carbon atoms linked together in chains and rings and three-dimensional structures of extraordinary complexity. Without carbon, the chemistry of life as we understand it cannot even begin. Europa had the kitchen, it had the stove, but until Webb, we did not know whether it had any ingredients. Now we know it has carbon, and the carbon is coming from the ocean. To feel the weight of this properly, picture the ocean as it must be. 60 miles of dark water, completely sealed from any light source, under pressure so enormous that the deepest point of Earth's ocean would feel mild by comparison. At the bottom, a rocky seafloor that has not been seen by any instrument or eye. Above, 18 miles of ice pressing down. No currents driven by wind because there is no atmosphere in contact with the water. No seasons because no sunlight ever reaches this deep. No day and night cycle. Just darkness and pressure and chemistry running in silence for 4 billion years. Into this ocean, the rocky seafloor is slowly releasing whatever compounds form when warm rock meets cold, salty water. Carbon compounds among them. Those compounds dissolve in the water, become part of the ocean's chemistry, and over geological time, some fraction of them get carried upward through the mechanisms we will examine shortly, through the cracks and chaos events in the ice, and eventually reach the surface where Webb can read them. The receipt from the kitchen downstairs reads, "Carbon present, ocean chemically active, ingredients confirmed." But carbon was only the first ingredient Webb identified in that receipt. The second one had been partially spotted years earlier by a different telescope, but Webb confirmed it with a clarity that settled the debate. And this second chemical in its own way told an even more intimate story about what kind of ocean Europa is hiding. In 2019, a team using the Hubble Space Telescope published a paper reporting the detection of sodium chloride on Europa's surface. The detection was real but faint. Hubble could see it. Hubble could not say with full confidence what it meant. The signal was at the edge of Hubble's capability in the relevant wavelengths, and alternative explanations could not be fully ruled out. The result was noted. It was significant, but it was not settled. Sodium chloride is not an exotic compound. It is ordinary table salt, the same white crystals you shake onto food. Chemically, it is a molecule made of one sodium atom bonded to one chlorine atom. On Earth, it is the primary dissolved mineral in seawater. Our oceans are salty largely because sodium and chloride ions, released from rocks by water erosion over billions of years, have accumulated in the sea. Salt is what you get when liquid water spends a very long time in contact with certain kinds of rock. Finding sodium chloride on Europa's surface would mean one of two things. Either it was delivered there from outside, from some external source, or it came from inside, from a salty ocean that deposited it on the surface, the way an ocean on Earth leaves salt deposits on coastal rock faces where waves splash and evaporate. Hubble's detection was suggestive of the internal origin but not conclusive. Webb settled it. When Webb pointed at Tara Regio, the sodium chloride signal was unmistakable. Sharp, clear, concentrated in the chaos region in precisely the same spatial pattern as the carbon dioxide. The salt and the carbon were sitting on top of each other. They had the same distribution boundary. They were both most intense in the interior of the chaos region, and both faded as you moved outward into the older, smoother, more undisturbed surrounding ice. Two chemicals, same location, same pattern, same conclusion. Both the salt and the carbon came from below. Both were deposited by ocean material being pressed up through the chaos terrain. The ocean beneath Tara Regio is chemically active, salty, and rich in carbon compounds. And it has been delivering that chemistry to the surface recently enough for the signals to still be readable through Jupiter's radiation damage. Richard Cartwright of Johns Hopkins Applied Physics Laboratory, who has spent years studying Europa's surface chemistry, described the chemical profile of this region as strange and exciting. That phrasing was deliberate. Cartwright is a spectroscopist, a scientist whose entire professional vocabulary is built around the precise description of molecular signatures. When a spectroscopist calls something strange, they do not mean aesthetically unusual. They mean the data does not fit the models. The models said one thing, the surface says another, and the surface wins. What Cartwright found strange was not simply the presence of sodium chloride, but its composition relative to what models predicted. Based on calculations of how Europa's rocky mantle should weather over billions of years in contact with a salty ocean, the surface should show significant amounts of magnesium-rich salts alongside the sodium chloride. The magnesium signature was weaker than expected. The sodium chloride dominated in a way that suggests the ocean's chemistry has been shaped by something specific, either an unusual seafloor rock composition or active hydrothermal processing that has preferentially mobilized certain minerals over others, or both. The ocean, in other words, is not generic. It is not simply a bathtub of water sitting on undifferentiated rock. It has a chemical personality. It has been shaped by billions of years of interaction with its own environment. It has a history written in its mineral content. And that history, however partially, is now readable on the surface above it. Now combine the salt and the carbon into a single picture, an ocean that is salty in a way that resembles Earth's deep seas more than anyone had anticipated, an ocean that contains carbon, the foundational building block of biology, an ocean that is actively communicating with the surface above it through the chaos terrain, delivering its chemistry upward where instruments can read it, an ocean whose chemical leakage is fresh enough to survive on the surface, meaning the process is ongoing, not ancien. Before Webb, the case for Europa's ocean being habitable was circumstantial. Liquid water? Yes. Energy source? Yes. Chemistry? Unknown. After Webb, the chemistry question has a partial answer. The ocean contains carbon. The ocean contains salt. The ocean's mineral profile suggests active geological processing. Every one of those facts moves Europa closer to the profile of a place where life as we understand it could operate. Astrobiologists have a checklist: liquid water, energy, carbon, nitrogen, phosphorus, sulfur, stable conditions over long time periods. Europa checks the first three items with confirmation. The remaining items are suspected, but not yet confirmed. The checklist is not complete, but it is longer now than it was before Webb looked. There is a way to picture what Webb actually accomplished with those few minutes of telescope time. Imagine you are standing outside a restaurant at night and the windows are frosted over. You cannot see inside, but through a small clear patch in the frost, you can make out a warm glow. The smell of cooking comes through a crack in the door, and a sound that might be conversation or might just be the hum of equipment. You cannot confirm that anyone is eating dinner inside, but you know the kitchen is on, you know food is being prepared, the building is not empty. Webb found the warm glow, it found the smell of cooking through the crack. Whether anyone is sitting at the tables inside is still unknown, but the kitchen is on, and the ingredients on the menu include carbon and salt, in a recipe that on our own planet has only ever been associated with one outcome. The salt and the carbon were the headline discoveries from Webb's first Europa observations, but the data contained a third finding, one that took longer to understand, and whose implications turned out to be in some ways even more significant. It was a finding about a chemical most people associate with medicine cabinets and cleaning products, a simple molecule that fizzes on a cut and whitens laundry. On Europa, it does something far stranger. It points to a possible source of energy that could power an entire biosphere. The molecule is hydrogen peroxide. Hydrogen peroxide forms on Europa's surface when Jupiter's radiation splits water molecules apart and some of the fragments recombine in specific ways. This has been known for years. The interesting question was always where on Europa's surface you would find the most of it. The established prediction, based on straightforward chemistry and temperature considerations, was that hydrogen peroxide should accumulate most heavily at the poles. The poles are colder. Hydrogen peroxide is more stable at lower temperatures. The poles also receive radiation at shallower angles, which means the particles penetrate the ice differently. Every model ran through before Webb pointed to the poles as the hydrogen peroxide hotspot. Webb checked. The poles were not the hotspot. The highest concentration of hydrogen peroxide Webb detected was at the equator. Specifically, it was concentrated in and around Terra Regio, the same chaos region where the carbon dioxide and sodium chloride were also concentrated. The warmer equatorial region, which by simple chemistry should have had less stable hydrogen peroxide, had more. The colder polar regions, which should have been accumulating hydrogen peroxide for billions of years, had less. The prediction was not slightly off, it was inverted. The team checked the instruments, they reprocessed the data. The result held. Hydrogen peroxide was abundant at the equator, and the leading explanation, the one that had seemed almost obvious before, was wrong. For more than a year after Webb's observations, this inversion sat in the data as an unexplained puzzle. Then, in 2024, a graduate student named Bereket Mamo at the University of Texas at San Antonio, working in collaboration with the Southwest Research Institute, decided to test a hypothesis in the laboratory. He cooled water ice down to Europa's surface temperatures. He added trace amounts of carbon dioxide, the same amounts Webb had detected. Then, he irradiated the ice with a particle beam calibrated to simulate Jupiter's radiation environment. The result was striking. The presence of even small amounts of carbon dioxide in the ice dramatically increased the rate of hydrogen peroxide production. The CO2 was acting as a catalyst, opening chemical reaction pathways that did not exist in pure water ice. More CO2 meant more hydrogen peroxide per unit of radiation. The two chemicals were not independent, they were coupled, they were amplifying each other. This solved the geographical puzzle entirely. The hydrogen peroxide was concentrated at the equator because the carbon dioxide was concentrated at the equator, delivered there from the ocean through Terra Regio. Wherever carbon from the ocean was reaching the surface, it was also supercharging the radiation chemistry, producing hydrogen peroxide at higher rates than the polar ice, which had no such carbon boost, could match. The equatorial hotspot was not a mystery, it was a consequence of the ocean's carbon chemistry reaching the surface and changing the rules of the photochemistry above it. But solving this puzzle opened a far larger one, because hydrogen peroxide is not merely an interesting chemical curiosity on Europa's surface. It is an oxidant, and the word oxidant, in the context of astrobiology, carries enormous weight. On Earth, complex life is powered by oxidation. Your cells right now are combining the oxygen you breathe with the food you have eaten, releasing the energy that keeps your heart beating, your neurons firing, your body warm. The oxygen is the oxidant. It provides the chemical driving force that makes the energy release possible. Without oxidants, you cannot have animals. Without oxidants, you cannot have most of the complex biology on this planet. The tree of life on Earth is fundamentally an oxidation machine, and it runs on the oxygen produced by photosynthesis in the sunlit upper layers of the ocean and atmosphere. Europa's ocean has no sunlight. The ice shell is 18 miles thick. No photon of visible light has ever reached the water below. Photosynthesis cannot happen there, and without photosynthesis, there is no obvious source of oxidants for the ocean. Without oxidants, the energy budget for any potential life is severely limited, unless something is delivering oxidants from above. This is where the hydrogen peroxide discovery becomes profound. The surface of Europa is constantly producing hydrogen peroxide and other oxidants driven by Jupiter's radiation. That radiation is unrelenting. It never stops. It has been generating oxidants on the surface for 4.5 billion years. If any mechanism exists to carry those surface oxidants down into the ocean, then the ocean is not cut off from oxidant chemistry. It has access to a continuous supply delivered from above by the relentless particle radiation of the largest planet in the solar system. And Webb has shown us that material is moving between the surface and the ocean. The chaos terrain is the mechanism. When the ice breaks and reforms in events like those that created Terra Regio, surface material gets folded down, subsurface material gets pushed up. The exchange is slow by human standards. It is not a rapid river current. It is a geological process, measured in millions of years. But over 4 billion years, even a slow exchange accumulates. If oxidants from the surface are being gradually delivered to the ocean through chaos terrain cycling, then the ocean has access to chemical energy from two directions simultaneously. From below, hydrothermal vents on the seafloor providing heat and reduced minerals. From above, oxidants sinking slowly through the ice exchange. Life on Earth uses exactly this combination, fuel meeting oxidant, to generate energy. The meeting of the two is what drives metabolism. Europa might not just be habitable, it might be powered in both directions at once. There is a detail in Webb's data that reinforces the picture of a dynamically active surface, one that took a separate team to fully interpret. Webb detected two forms of the same ice on Europa's surface, existing side by side in the chaos regions, and the fact that both were present simultaneously should have been impossible if the surface were old and static. Water ice can freeze in two fundamentally different ways. When water freezes slowly, under stable conditions, the molecules have time to arrange themselves into a regular repeating pattern, locking into a crystalline structure. This is crystalline ice. It is the kind you find in your freezer, in snowflakes, in glaciers. The molecules are ordered. They form a lattice. When water freezes quickly, or when existing crystalline ice is bombarded by high-energy radiation, the molecules do not have time to find their ordered positions. They freeze in whatever arrangement they happen to be in at the moment of transition, a disordered jumble with no repeating pattern. This is amorphous ice. Its molecules are frozen in chaos rather than order. On a moon bathed in Jupiter's radiation, the expectation was clear. Radiation converts crystalline ice to amorphous ice continuously. Given enough time, every patch of surface should be amorphous, its ordered structure long since scrambled by billions of years of particle bombardment. Crystalline ice, if it ever formed, should be erased within thousands to tens of thousands of years. Webb saw crystalline ice and amorphous ice coexisting in the chaos regions. A team led by Ujjwal Raut at the Southwest Research Institute reported this finding, published in 2025. They had not been specifically looking for it. The spectral data simply showed both signatures simultaneously in the same locations. They checked. They reprocessed. The result was real. The only way to explain the presence of crystalline ice in a radiation environment that should have destroyed it is if the surface is being continuously renewed. Fresh, crystalline ice is being produced faster than radiation can convert it to amorphous ice. This renewal can happen in two ways. Either the surface is being periodically warmed, perhaps by the concentrated tidal heating beneath Terra Regio, to temperatures that allow the ice molecules to reorder themselves before being re-scrambled, or fresh water is being delivered from below, freezing into crystalline form as it reaches the surface, and being detected by Webb before the radiation has finished processing it. Either mechanism tells the same story. The surface of Europa is not a museum, it is a renovation project in progress. Material from the interior is reaching the surface continuously, refreshing the chemistry, refreshing the ice structure, overwriting the radiation damage before it can fully accumulate. This has a profound implication for the search for life. Any chemical signatures we detect on Europa's surface today are not relics of the ancient past. They are dispatches from the present. They reflect what the ocean is doing right now, or at least within the last few million years, which, in the context of a 4-billion-year-old system, is effectively the present tense. Webb is not reading a 4-billion-year-old letter. It is reading today's mail, and today's mail says the ocean is chemically active, carbon-rich, salty, producing oxidants at the surface, and refreshing its own chemistry through the chaos terrain with a regularity that suggests the process has never truly stopped. From the first moment Europa's tidal engine turned on, this exchange has been running, quietly, continuously, in complete isolation from everything else in the universe, for 4.5 billion years. In the dark, 60 miles below the surface of Europa, past the ice shell and past the full depth of the ocean, there is a seafloor. We have never seen it. No instrument has directly measured it. No photograph of it exists. Everything we know about it has been inferred from the moon's total mass, its density profile, the way it responds to Jupiter's gravitational pull, and the chemical signatures that leak upward through the water and ice above it. In the entire history of human exploration, no place we have reason to believe might harbor life has ever been more completely hidden from us. And yet, what we can infer about that seafloor, combined with what Webb has now confirmed about the ocean above it, makes it the most scientifically consequential real estate in the outer solar system. To understand why, you have to go back to a moment on Earth that permanently changed how scientists think about life. Not a moment in the distant past, when early cells were forming in ancient seas. A moment that happened within living memory on a specific day, at a specific depth, in a specific part of the Pacific Ocean, when two scientists inside a submersible saw something that had no right to exist. The year was 1977. The submersible was called Alvin. It belonged to the Woods Hole Oceanographic Institution in Massachusetts, and it had been diving to the deep ocean floor for years, as part of a geological survey of the mid-ocean ridges, the vast underwater mountain ranges where tectonic plates pull apart, a new seafloor is created. The scientists on this particular dive were geologists. They were looking for evidence of hydrothermal activity, places where seawater seeps into cracks in the seafloor, gets heated by the underlying volcanic rock, absorbs minerals from the surrounding stone, and then erupts back into the cold water above as superheated, mineral-rich plumes. They expected to find interesting geology. They did not expect to find life. At a depth of roughly 8,000 feet in the Galapagos Rift, Alvin's exterior lights illuminated something that stopped the dive team completely. Surrounding the hydrothermal vents, in water that no sunlight had ever touched, in pressure that would crush an unprotected human body, in heat that fluctuated from near freezing in the surrounding water to several hundred degrees Celsius at the vent mouths themselves, was life. Not sparse bacterial films, not a few hardy microbes clinging to the rocks, an entire ecosystem. Tube worms up to 8 feet long, clustered in dense colonies around the vent chimneys, white crabs picking their way across the seafloor, mats of bacteria covering every surface, clams and mussels and shrimp in varieties no one had catalogued, a complete food web thriving in absolute darkness, powered by chemistry rather than sunlight. The scientists on board reportedly stared in silence for a long moment before anyone spoke. The vent ecosystems proved this wrong. Here was an entire biosphere that had never received a single photon of sunlight. Its energy source was chemical. The bacteria at the base of the food chain were not photosynthesizers, they were chemosynthesizers. They drew energy from the chemical reactions occurring when hydrogen sulfide and other compounds released by the hot vents met the cold, oxygen-bearing seawater above. The tube worms did not eat the bacteria directly. They housed them inside their own tissues in a partnership so intimate that the worms had no digestive system at all. The bacteria lived inside the worm. The worm provided shelter and access to both the sulfide-rich vent water and the oxygen-rich surrounding water. The bacteria did the chemistry, the worm got the energy. This kind of relationship, this deep biochemical partnership between organism and chemistry, was not an edge case. It turned out to be widespread. As deep-sea exploration expanded in the decades following 1977, vent ecosystems were found on every mid-ocean ridge that was searched, in the Atlantic, in the Indian Ocean, in the Arctic, under the Antarctic ice. Everywhere the conditions were right, life had found them and moved in. The vents were not rare exceptions to biology's rule. They were an entirely parallel track of life that had been operating in silence since long before anything breathed oxygen on the surface. Some researchers went further, looking at the chemistry of deep hydrothermal vents and comparing it to the chemistry believed to characterize the early Earth. Before there was any life at all, they began to argue that vents were not just places where life survived. They were places where life began. The combination of warm, mineral-rich water, chemical gradients between hot and cold, and the physical structure of the vent chimneys themselves created natural chemical reactors that could have produced, over millions of years of continuous experiment, the first self-replicating molecules. This idea, known as the hydrothermal vent origin of life hypothesis, is today one of the two leading theories for how life started on Earth. The other proposes warm, shallow surface pools struck by lightning and ultraviolet light. Both remain active areas of research. Neither has been definitively confirmed. But the vent hypothesis has gained ground steadily in recent decades, supported by studies showing that vent chemistry naturally produces amino acids, fatty acids, and other biological precursors under conditions that could have existed on early Earth without any guidance from biology. The implication that follows from all of this took time to fully register in the scientific community. If life can start at a hydrothermal vent, and if life needs nothing more than liquid water, chemical energy, and the raw molecular ingredients, then the origin of life is not a story about Earth. It is a story about chemistry. And chemistry does not need a specific planet. It needs specific conditions. Those conditions are not rare. Those conditions exist, right now, at the bottom of Europa's ocean. Walk through the comparison carefully, because every element of it matters. 4 billion years ago, the early Earth had a surface that was hostile to life by any modern standard. The atmosphere contained almost no free oxygen, volcanic eruptions were frequent and violent. Meteorite impacts were still common. The sky was dim because the young sun was approximately 30% fainter than it is today. No plants existed, no soil existed. The surface was a chemical wasteland by any reasonable definition. But at the bottom of the early Earth's oceans, near hydrothermal vents on the rocky seafloor, the conditions were very different. The water was liquid, the chemistry was rich. The vents were releasing hydrogen, sulfur compounds, carbon dioxide, and a spectrum of dissolved minerals into the surrounding water continuously, providing both the raw materials and the energy gradients that chemistry needs to do interesting things. The physical structure of the vents, with their porous mineral chimneys creating thousands of tiny compartments at different temperatures and chemical concentrations, provided natural reaction vessels where molecular experiments could run in parallel, simultaneously, without interruption, for millions of years. Somewhere in that vast parallel experiment, the chemistry produced a molecule that could copy itself. That molecule is the ancestor of every cell on Earth. Now stand at the bottom of Europa's ocean. The water is liquid, the depth is 60 miles. The pressure is immense but not prohibitive for chemistry. The temperature near the seafloor if hydrothermal vents are active, could range from near freezing in the open water to several hundred degrees Celsius at the vent mouths, the same range that exists at Earth's deep-sea vents. The rock below has been in contact with salty water for 4.5 billion years, the same length of time the early Earth spent building up to its first life. Webb has confirmed that carbon is present in the ocean. The magnetic readings from Galileo confirmed that the water is salty. The tidal heating from Jupiter provides a continuous energy source to drive rock-water reactions at the seafloor. Every ingredient that researchers believe was present at Earth's primordial vents is inferred to be present at Europa's seafloor. Not approximately, not loosely. The same liquid water, the same carbon, the same salts, the same chemical energy from rock-water interaction, the same time available for the experiment to run. The only meaningful difference between early Earth's hydrothermal vents and the inferred conditions at Europa's seafloor is that we are not certain Europa's vents are currently active. We have never seen them. We have never measured them directly. We have only the indirect evidence of the ocean's existence and the chemical signatures leaking upward through the ice. But consider what that indirect evidence actually says. An ocean that has been liquid for 4 billion years requires continuous heating. The tidal mechanism from Jupiter provides that heating, but tidal heating is not uniform. It concentrates in regions of the interior, where the rock is under the most stress. Those regions are where the rock is hottest. Hot rock in contact with salty ocean water produces hydrothermal activity, the same physics that drives hydrothermal vents on Earth. The combination of heat, rock, and liquid water is operating at Europa's seafloor right now by every physical principle we understand. We cannot confirm the vents are there without going there, but their absence would require an explanation, and no such explanation exists in our current models. The chemical signatures Webb found on the surface reinforce the case. The specific mix of compounds detected, the carbon dioxide with its internal isotope ratio, the sodium chloride with its unusual dominance over magnesium salts, the overall chemical profile of Tara Regio, is consistent with what you would expect if the ocean had been chemically shaped by long-term interaction between liquid water and a rocky seafloor under thermal stress. On Earth, hydrothermal vent water has a distinctive chemical signature. It is enriched in certain metals, depleted in others. It carries specific sulfur compounds. It has characteristic ratios of different elements that reflect the particular rock type it has been interacting with and the temperatures it has experienced. Scientists who study vent chemistry can look at a sample of vent water and read its history in the proportions of its dissolved minerals. Europa's surface leakage, read by Webb from 400 million miles away, does not perfectly match any specific Earth vent system. The comparison is not that precise and cannot be. But the general profile, carbon-rich, salt-dominated, with the particular balance of minerals that Webb detected, fits the category of chemistry you would expect from a water body that has spent billions of years processing rock at elevated temperatures. The ocean smells, chemically speaking, like it has been cooking on a stove. Now add the oxidant picture from the previous chapter. The hydrogen peroxide Webb detected on the surface, supercharged by the carbon dioxide, represents a potential supply of chemical energy from above. The vents, if active, represent a supply of chemical energy from below. Life in Europa's ocean, if it exists, would be sitting between two energy sources simultaneously. Reduced minerals from the hot rock below, oxidants sinking slowly from the surface above. The meeting of reductants and oxidants, of fuel and the chemical force needed to burn it, is the fundamental transaction of biochemistry. Every organism that has ever lived on Earth draws its energy from exactly this kind of transaction. Europa may be running it in both directions at once. To make this concrete, imagine a sealed room with a furnace in the floor and a ventilation system in the ceiling that slowly pumps in a supply of fresh air. The furnace provides heat and fuel, the air provides oxidant. An organism living in that room would have everything it needs to carry out the chemical reactions that drive metabolism. It would not need sunlight. It would not need the outside world at all. It could live indefinitely in that sealed room as long as the furnace kept running and the ventilation kept working. Europa's ocean is that sealed room. Jupiter's tides are the furnace. The chaos terrain cycling of oxidants from the surface is the ventilation. The chemistry has been running for 4 billion years. Whether anything alive is running on it is the question we cannot yet answer. The parallel between early Earth and Europa goes beyond chemistry. It extends to time. Life on Earth did not appear instantly. The earliest evidence for life, microbial mats preserved in ancient rock formations in Western Australia and Greenland, dates to approximately 3.5 to 3.8 billion years ago. The Earth itself is 4.5 billion years old. That means life appeared, as best we can tell from the geological record, within roughly the first billion years of the planet's history. Perhaps within the first few 100 million years, if the controversial evidence of biological carbon isotope signatures in ancient minerals is accepted. From a cosmic perspective, that is fast. The conditions were established, the chemistry ran, and life appeared in what amounts to a geological eye blink. The speed at which life appeared on Earth, once the conditions were right, has led many researchers to conclude that the origin of life is not a fantastically improbable accident, but a chemically inevitable outcome given the right starting conditions. Given enough liquid water, enough carbon, enough energy, enough time, the chemistry of life will emerge. Europa has had the right starting conditions for approximately 4 billion years. Not a few 100 million, 4 billion. If the origin of life is a chemical inevitability under the right conditions, then Europa has had 4 times longer than Earth needed to achieve it. The counter-argument is that we do not actually know how difficult the origin of life is. We have exactly one example. We cannot compute the probability of life arising from chemistry because we have never seen it happen from scratch. Earth's single instance tells us it happened once, but gives us no statistical framework for knowing how often it happens in general. It could be nearly inevitable given the right conditions. It could be a 1 in a trillion accident that happened to go right once on the one world we happen to live on. This uncertainty is honest. It is not a dismissal of the question. It is an acknowledgement that the question is harder than it looks. The origin of life problem is one of the deepest unsolved problems in all of science, not because researchers have not been working on it, but because the machinery of early life has been obscured by billions of years of subsequent evolution. We are trying to reconstruct the first page of a 4 billion-year-old story, from which most of the early pages have been lost. What we can say with confidence is this: every condition that early Earth is believed to have had at its hydrothermal vents, the conditions that researchers believe may have produced the first cells, is inferred to exist right now at Europa's seafloor. If those conditions are sufficient to produce life, then Europa's ocean has had more than enough time to find out. There is a deeper implication in this parallel that is rarely stated directly, but that underlies the entire scientific urgency surrounding Europa. It is about what the answer would mean, regardless of which way it falls. If Europa has life, even microbial life, even the simplest possible form of chemistry that counts as biological, then life arose twice in the same solar system, independently, in parallel, starting from the same basic chemistry on 2 worlds that never made contact with each other. The implications of that single fact radiate outward in every direction. 2 independent origins of life in one solar system means that the origin of life is not a rare accident. It is a common outcome. It is what chemistry does when given the right conditions and sufficient time. And if that is true of the solar system, it is true of the galaxy. The Milky Way contains somewhere between 200 and 400 billion stars. A significant fraction of them have planets. A fraction of those planets have moons. A fraction of those moons are ocean worlds kept warm by tidal heating from their parent planet. If life arises wherever the conditions are right, then the galaxy is full of it. Not rare islands of biology in a sterile universe. A vast, distributed, mostly microbial tapestry of life woven through every system where the chemistry is favorable. The universe is not empty. The universe is inhabited. That would be the most profound scientific discovery in the history of human civilization. It would not merely add a data point to our knowledge of the cosmos. It would fundamentally redefine what the cosmos is. If Europa is dead, the implication runs the other direction and is in its own way equally profound. If a world with liquid water, carbon, salt, chemical energy, and 4 billion years of stability produces no life, then the conditions we believe are sufficient for life are not actually sufficient. Something is missing from our model. Some ingredient, some condition, some physical or chemical or perhaps quantum mechanical factor has not been identified. Life on Earth may be a singular event, an accident so improbable that despite a universe of a trillion stars and a billion years of cosmic time, it happened only once. We would be alone, truly alone, not alone in the sense that no other life has evolved yet, or that we have not found it yet. Alone in the deep structural sense, the only experiment that went right in the entire history of a universe 15 billion years old. Neither answer is small. Neither answer permits things to continue as they were before. There is no neutral outcome when you ask whether Europa is alive. There is only the two most consequential answers the universe has ever offered to a question asked by a species on a small planet in an ordinary star system on an unremarkable arm of one of hundreds of billions of galaxies. We have been asking the question for decades. The instruments to begin answering it are either already pointed at Europa or already on their way. Before we follow those instruments to what they are about to find, there is one more piece of the seafloor story that needs to be told. It concerns the precise mechanism by which oxidants from the surface might reach the deep ocean, because the path is not a simple pipe. It is a slow, complicated geological conveyor belt. And understanding it changes how we think about the habitability of worlds sealed under ice. Webb's detection of crystalline and amorphous ice side by side in the chaos regions established that the surface of Europa is being continuously refreshed from below. Material from the ocean is reaching the top, but the exchange is not one-directional. If material is coming up, the physics of a convecting ice shell suggests that material must also be going down. Picture the ice shell as a very slow fluid, not fluid in the sense that you could swim through it, but fluid in the sense that on timescales of millions of years, the ice behaves like a viscous material, flowing and circulating under the influence of the temperature gradient between the warm ocean below and the cold surface above. Warm ice near the ocean is slightly less dense than cold ice near the surface. It rises slowly. Cold surface ice sinks slowly. The whole shell circulates in a process called convection, the same process that drives weather in Earth's atmosphere and tectonic movement in Earth's mantle. If the ice shell is convecting, then surface material, including the oxidants generated by Jupiter's radiation, is being carried downward by the sinking cold ice. Over millions of years, the oxidants generated at the surface accumulate in the ice, get transported slowly downward through the convecting shell, and eventually reach the base of the ice, where they can mix into the ocean water. This mechanism, if it is operating, would give Europa's ocean access to a continuous supply of oxidants from above, independent of chaos terrain events. It would not require catastrophic ice breakup to deliver chemistry from the surface to the ocean. It would happen quietly, continuously, through the normal circulation of a convecting ice shell. We cannot confirm that convection is occurring. The evidence is circumstantial, but scattered across Europa's surface are small, roughly circular features called lenticulae, Latin for lentils, because that is what they look like from orbit. Some are domes rising above the surrounding surface. Some are pits sinking below it. Some are flat, featureless patches with no obvious topographic relief. They range from a few miles to a few dozen miles across, and they are distributed across the entire moon in a pattern that resists simple geological explanation. The leading theory for their formation is exactly this: warm blobs of ice rising through the shell from below, driven by convection, reaching the upper layers, pushing the surface upward into domes or melting it from beneath into pits, and then cooling and sinking back down. Each lenticular is a frozen snapshot of one of these convective events, a moment when the slow circulation of the ice shell briefly broke through to the surface. If lenticulae are convection signatures, then Europa's ice shell is alive in a geological sense that no simple frozen lake ever is. It is being continuously reworked from within. Surface material is being slowly carried down. deep material is being slowly carried up. The two ends of the system, the radiation-bathed surface and the dark, chemically rich ocean, are in slow, continuous communication. And that communication is what makes Europa's ocean not just a body of water, but a chemical system with inputs from multiple sources and a metabolism of its own. Not biological metabolism, geological metabolism, but the structure of the system, with energy in from below, oxidant energy in from above, chemical cycling through the medium of the ice, is organized in a way that life on Earth would recognize and, under the right circumstances, exploit. The seafloor we have never seen is driving this entire system from the bottom. Everything above it, the ocean's chemistry, the chaos terrain events, the surface deposits that Webb is reading, the convecting ice shell, all of it flows from the single fact that at the base of 60 miles of dark water, rock is being heated by Jupiter's gravity, and that heat is driving chemistry. That chemistry has been running, quietly and continuously, in total isolation from the rest of the universe, for 4.5 billion years. Long before the first cell appeared on Earth, the vents at Europa's seafloor may already have been running. Long before the first fish swam in Earth's oceans, the water above Europa's vents may already have been full of whatever it is full of. Long before humans looked up at Jupiter and wondered what its moons were, the experiment at the bottom of Europa's ocean had been running patiently, without any need for an observer, for longer than life has existed on Earth. We are late to this story. The chemistry started without us. Whether it has produced anything we would recognize as alive is the question we are finally, after all this time, close enough to the answer to begin truly asking. Most people, when they imagine the ice shell of Europa, picture something like the frozen surface of a lake in winter, solid, uniform, a clean barrier between the air above and the water below. You could walk across it. You could drill through it if you had the right equipment. The boundary between the two worlds, the surface and the ocean, would be sharp and clearly defined. Europa's ice does not work that way. What Webb's chemical findings, combined with close flyby data from the Juno spacecraft and decades of surface imaging from the Galileo mission, have collectively revealed is something far stranger. The ice shell of Europa is not a clean wall. It is a porous, fractured, dynamically active material that is being continuously reworked from within. It has internal structure. It has warm regions and cold regions. It has cracks that extend downward for miles. It has pockets of liquid water trapped within its own thickness. It has a surface that is being erased and rewritten on timescales that are short by geological standards. And it breathes, not in the biological sense. In the geological sense, it exhales chemistry from the ocean below and inhales radiation products from the surface above, slowly, continuously, on a cycle that has been running since the shell first formed. Understanding this breathing is essential to understanding what Europa actually is. And understanding what Europa actually is determines whether any spacecraft we send there can find the answer we are looking for without drilling 18 miles through solid ice. The data that most directly addressed the ice shell's internal structure came from a spacecraft that was not designed to study Europa at all. Juno launched from Cape Canaveral in August of 2011 and arrived at Jupiter in July of 2016. Its primary mission was to study Jupiter itself, specifically the planet's deep interior, its magnetic field, and the dynamics of its enormous atmosphere. Juno was built to solve fundamental questions about how Jupiter formed, how its storms are structured at depth, and how the largest planet in the solar system has shaped the rest of the solar system around it. For most of its early mission, Juno stayed close to Jupiter, diving in and out of the planet's radiation belts on a highly elliptical orbit that kept it away from the major moons. Then, in September of 2022, its orbit was adjusted and Juno performed a close flyby of Europa, passing within roughly 220 miles of the moon's surface. A second close flyby followed in late 2024. During both passes, Juno's instruments were recording everything they could detect. One instrument in particular turned out to be unexpectedly useful for Europa science. The microwave radiometer, originally designed to peer into Jupiter's cloud layers by measuring the natural microwave emission at different depths in the atmosphere, also turned out to be capable of peering into Europa's ice. Microwaves penetrate ice in a way that visible light and infrared cannot. Different temperatures and different structural features within the ice reflect or scatter microwaves differently. By carefully analyzing the pattern of microwave signals bouncing back from Europa during the flybys, it was possible to map the thermal and structural properties of the upper ice shell to a depth of hundreds of feet below the surface. The team led by Stephen Levin at NASA's Jet Propulsion Laboratory published their results from the Juno flybys in the journal Nature Astronomy in December of 2025. What they found added a crucial physical dimension to the chemical story Webb had already told. The first major finding confirmed what models had long predicted, but never directly measured. The ice shell is approximately 18 miles thick on average, with an uncertainty of roughly 6 miles in either direction. This is in the middle of the range that various indirect methods had previously estimated. It is thick enough to make direct drilling from a spacecraft essentially impossible with any technology that exists or is likely to exist within the next several decades. But it is thin enough that geological processes, operating over millions of years, can and do transport material between the ocean and the surface. The second finding was more surprising and more immediately useful for understanding how Europa works. The microwave data showed extensive scattering within the upper ice. The microwaves were not passing cleanly through a uniform block of frozen water and bouncing back from a smooth lower surface. They were being deflected by countless small features scattered throughout the upper hundreds of feet of ice. Features that were too small to be individual cracks or cavities of any significant size, but that were present in such numbers that their collective effect was substantial. The Juno team's interpretation was that Europa's upper ice is riddled with tiny pores, bubbles, and microfractures, not large enough to see individually, not large enough to create pathways for liquid water to flow through, but present everywhere, woven through the fabric of the ice, like the countless tiny air pockets in a foam material, creating a texture that is structurally very different from the clean, transparent ice of a frozen lake. To picture this properly, hold two objects in your mind simultaneously. The first is a block of clear ice, the kind that forms when water freezes slowly and cleanly in a freezer. You can see through it. It is dense and uniform. If you shone a light through one side, it would come out the other side, with minimal scattering. The second object is the kind of cloudy, white ice that forms when water freezes quickly or when a glacier compresses snow over many years. You cannot see through it. The light that enters it bounces off countless internal interfaces and emerges scattered in all directions. The ice is full of tiny structures that make it opaque. Europa's upper ice is the second kind, dense and strong but internally complicated, full of microstructure, not a clean window but a frosted one. This finding matters for two reasons that pull in opposite directions. The first is a limitation. The Juno team concluded that the tiny pores and microfractures in the upper ice are probably too small and too shallow to act as physical channels for large-scale transport between the surface and the ocean. Liquid water cannot flow easily through pores measured in millimeters or centimeters. Microorganisms, even very small ones, would have no pathway to swim upward through such tiny gaps. The microstructure of the upper ice is not a highway between the surface and the ocean. It is more like a sponge, permeable to gases and dissolved compounds moving slowly by diffusion over geological time, but not permeable to bulk fluid flow or to anything with physical size. For the dream of directly sampling Europa's ocean from the surface, this is a sobering finding. You cannot simply land and scoop up a bucket of fresh ocean water that has percolated up through the ice. The microfractures are too small for that. The second implication, however, is more encouraging and connects directly to Webb's chemistry findings. Gases and dissolved compounds do not need large channels to migrate through ice. Given enough time, molecular diffusion can carry chemical species through a porous medium even when the pores are tiny. Carbon dioxide, a gas at room temperature, though frozen into the ice at Europa's surface temperatures, can migrate through microfractured ice over millions of years. Dissolved salts can move through brine films that form along the boundaries between ice crystals, even at temperatures well below the bulk freezing point of water. The microstructure Juno detected does not block the slow chemical communication between the ocean and the surface. It merely ensures that communication happens gradually and diffusely, rather than through dramatic eruptions. The ice breathes not through lungs but through skin. The chemistry seeps rather than flows. And the chemistry that Webb detected on the surface, the carbon dioxide and the sodium chloride concentrated in Terra Regio, is consistent with exactly this kind of slow seepage, supplemented by the larger scale chaos terrain events that periodically bring bigger volumes of ocean material close to the surface. Together, Juno's structural picture and Webb's chemical picture fit the same model: a thick, porous, internally active ice shell that allows slow chemical exchange everywhere and faster, more dramatic exchange at specific locations where the shell has been disrupted from below. Not a sealed vault, a breathing wall. The chaos terrains are where the breathing becomes most visible, and to understand the full picture of how the ice shell works, you have to understand not just what chaos terrain is, but how it forms, because the mechanism of formation is itself a window into the deep interior. Connemara chaos is one of the largest and most studied chaos regions on Europa. It sits near the Moon's equator and covers an area roughly the size of the state of Massachusetts. When the Galileo spacecraft photographed it in the late 1990s with the best cameras available to planetary science at the time, the scientific community's first response was confusion. They had expected to find icy plains with some cracking. They found something that looked, in the words of one researcher at the time, like a frozen disaster. The surface of Connemara is broken into dozens of flat-topped ice blocks, each several miles across, sitting at slightly different heights and orientations relative to their neighbors. Between the blocks runs a darker, rougher material that appears to have once been fluid before freezing in place. Some of the blocks have been rotated from their original positions, a few appear to have been flipped. The geological record preserved in the pattern of the cracks and ridges on the individual block surfaces can be read like a puzzle, and when you piece it together, the blocks fit back into their original arrangement before the disruption, like reassembling a broken plate by sliding the shards back into place. The picture that emerges from the reconstruction is this: at some point in the geological past, the ice in this region was broken apart from below. The upper layer of the shell fractured into pieces. Those pieces floated on a layer of slush or liquid water for a period of time, long enough for them to drift and rotate into their new positions. Then the whole region refroze, locking the displaced blocks permanently into their current arrangement. For that sequence to occur, the ice shell beneath Connemara had to soften or partially melt catastrophically over a large area. The ocean below had to rise, or warm material within the ice had to migrate upward with enough energy to disrupt a region the size of a state. Either the ocean itself briefly broke through the base of the shell at this location, or a warm blob of ice, driven upward by convection, reached the upper layers and released enough heat to melt the base of the overlying shell. Connemara is estimated, based on crater counting, to be geologically young, perhaps tens of millions of years old in a moon that is 4.5 billion years old. In relative terms, Connemara is as fresh as a wound that opened yesterday, and there are dozens of chaos regions on Europa, each one representing a separate event, a separate moment when the interior pushed hard enough against the shell to break it. The pattern is not random. Chaos regions are not distributed evenly across Europa. They cluster in certain latitudinal bands and appear to be associated with regions where tidal heating is concentrated by the interaction between Europa's slight interior asymmetry and Jupiter's gravitational field. The chaos regions mark the hotspots. They mark the places where Jupiter's mechanical energy is most efficiently deposited into the interior, where the ice is thinnest and warmest, and where the connection between the hidden ocean and the visible surface is most recently and most dramatically established. Webb's chemical target, Terra Regio, sits in this category. It is a chaos region in an equatorial zone where tidal heating models predict elevated energy deposition. When Webb's instruments revealed that the strongest chemical leakage from the deep ocean was concentrated precisely there, The finding was not coincidental. Terra Regio is chemically rich because it is thermally active. The same tidal energy that Jupiter pumps into this region of the ice shell is the energy that drives the chaos terrain formation and the chemical exchange that Webb is reading from 400 million miles away. The chaos regions are, in the clearest possible language, the places where Europa's interior is closest to its surface. They are the geological joints in the ice, the hinge points where the rigid outer shell has cracked and flexed and partially given way. And they are the natural targets for any spacecraft that wants to sample ocean chemistry without drilling 18 miles of ice. You do not need to reach the ocean directly. You need to find the places where the ocean has already reached you. Among the most physically unusual features on Europa's surface, and the ones whose origin is most directly connected to the question of whether the ice shell is convecting, are the double ridges. They are the most common geological feature on the Moon. Thousands of them cross the surface in every direction, some running for hundreds of miles in gently curving paths, others making sharp turns or crossing each other at intersections. They almost always appear as pairs, two parallel raised walls of ice, with a valley between them, like a very long highway median seen from a great height. The consistency of their form is itself a clue. Two parallel walls, a central valley, roughly symmetric profiles, the same basic geometry repeated thousands of times across the entire Moon. Whatever process makes one double ridge makes all of them. The mechanism is global. It is tied to something fundamental about how Europa's ice shell responds to stress. Several formation mechanisms have been proposed. One holds that double ridges form along deep cracks in the ice shell, where ocean water rises into the crack by tidal pumping, freezing along the edges as it goes, and gradually building up the parallel walls over many cycles of tidal flexing. Another proposes that the ridges form by compression along fault lines in the ice, with the two walls being pushed up on either side of the fault as the ice buckles under lateral stress. A third mechanism, suggested by a study published in 2022 by researchers at Stanford University, draws on a direct analogy with features observed in Greenland. The Greenland study used satellite data to identify small double ridges forming in the Greenland ice sheet, structures remarkably similar in form to Europa's ridges, though vastly smaller in scale. By monitoring the Greenland ridges over time and correlating their formation with known subsurface conditions, the team concluded that they formed when shallow pockets of liquid water trapped within the ice sheet refroze and expanded. The expanding water pushed up the ice above it on both sides of the pocket, creating a symmetric pair of raised walls, a double ridge, with the refrozen water pocket marking the central valley between them. If the same mechanism operates on Europa, and the geometric similarity is compelling enough that many researchers believe it does, then the double ridges are not just stress features in the ice, they are the surface signatures of water, liquid water pockets trapped within the ice shell itself, between the ocean below and the surface above, at depths shallow enough that their refreezing can push up the surface. Water inside the ice. Not the deep ocean, not surface melt water, water within the shell itself, at intermediate depth, existing in temporary liquid form before freezing and marking its former presence with a ridge on the surface above. If this interpretation is correct, then Europa's ice shell is not a simple two-layer system of ocean below and ice above. It is a three-layer system, ocean at the base, ice shell in the middle. But within that ice shell, distributed pockets of liquid water, temporary, unstable, forming and refreezing on timescales of thousands to millions of years, but present. These internal water pockets would be a different kind of habitable environment from the deep ocean, smaller, less stable, subject to eventual freezing, but also potentially accessible. A surface lander that could drill even a few tens of feet into the ice above a recent ridge might reach the frozen remnant of one of these pockets and sample its chemistry directly, not the deep ocean, but not just the surface either, an intermediate sample, carrying some fraction of the ocean's chemistry in a more accessible location. The double ridges have mapped these intermediate targets for us across the entire surface of the Moon. Thousands of potential sampling locations, marked in ice, waiting for a probe with a drill. Now return to the crystalline ice finding. because in light of everything the ice shell structure has revealed, its significance becomes even clearer. Ujwal Raut's team at the Southwest Research Institute, in reporting the coexistence of crystalline and amorphous ice in Europa's chaos regions, was documenting something that should be understood as a direct measurement of the ice shell's activity. The crystalline ice is not a relic. It cannot be. Radiation converts crystalline to amorphous ice on timescales of thousands of years. Any crystalline ice that is still crystalline today was either produced recently or has been continuously regenerated by processes that outpace the radiation damage. The only processes that could continuously regenerate crystalline ice on Europa's surface against the relentless radiation from Jupiter are processes that deliver fresh, warm water or warm ice from below. Fresh water delivered to the surface from the ocean below would freeze into crystalline ice. The ice in convecting blobs rising through the shell would be warm enough, relative to the surface, to recrystallize as they approach the top. Either mechanism requires an active, warm interior pushing material upward continuously. The crystalline ice is the fingerprint of that upward motion. It is the mark left on the surface by the interior's refusal to stay quiet. And it is being continuously made, not once in the geological past. Now, the ice web detected that is still crystalline was delivered to or recrystallized at the surface recently, enough to survive radiation damage. The interior is active today. The exchange between the ocean and the surface is not a relic of an ancient era when Europa was younger and warmer. It is a present tense process. This is one of the most important things Webb contributed to Europa science, not through any single dramatic detection, but through the cumulative picture built from multiple chemical and physical observations. Europa is not a world frozen in an ancient state. It is a world in ongoing geological motion, continuously exchanging material between its interior and its surface, continuously refreshing its own chemistry, continuously marking its own activity in the pattern of compounds that Webb can read from across the solar system. The question of whether life exists in Europa's ocean cannot be answered from the surface alone, but the question of whether the ocean is active, whether it has the chemical richness and the energy sources and the physical dynamism that life would need, can be substantially addressed from the surface. And the surface, as read by Webb and illuminated by Juno and mapped by Galileo, says yes to all of those questions. The ocean is active, the chemistry is rich, the energy is present, the exchange between the interior and the surface is ongoing. The ice is not a sealed lid. It is a breathing wall through which the deep interior announces itself continuously. Something is down there, something chemical at minimum. The chemistry is running, the vents are almost certainly active, the ingredients are confirmed. Whether the recipe has produced anything that breathes, in the biological sense, is the question that no instrument currently in operation can answer. But the instruments that might be able to answer it are already in motion. One of them launched in October of 2024. It will arrive at Jupiter in 2030. And it was designed specifically, precisely, and at extraordinary expense to ask Europa the question that all of this science has been building toward. The ice has been telling us its secrets slowly, through leakage and crystalline residue and doubled ridges and broken chaos fields. The next chapter of the story will be told not by a telescope looking from 1,000,000 miles away, or by a spacecraft flying past on its way to somewhere else, but by a probe that will spend years doing nothing but studying this single moon, flying past it again and again, reading it from every angle, with instruments 10 times more sensitive than anything that has approached it before. The ice has been patient. It has been that something is almost there. In October of 2024, a rocket climbed away from the Kennedy Space Center in Florida, carrying the largest, most complex, most expensive spacecraft ever built for the explicit purpose of studying a single moon. The spacecraft's solar panels, folded against its body during launch, would later unfurl to a span of nearly 100 feet from tip to tip, the largest solar arrays ever flown on a planetary science mission. They had to be that large because at Jupiter's distance from the Sun, sunlight is only about 4% as intense as it is at Earth. To power the instruments needed to do the science, the spacecraft needed to gather every available photon across a collecting area roughly the size of a modest house. Its name is Europa Clipper. The mission took more than a decade to move from concept to launch. At various points, it was threatened by budget constraints, by competing priorities, by technical challenges that required years of engineering work to solve. The radiation environment at Europa is so intense that ordinary spacecraft electronics would be degraded or destroyed within a few orbits. Europa Clipper's electronics are housed in a radiation-shielded vault, a thick-walled metal box at the center of the spacecraft that protects the most sensitive components from Jupiter's particle bombardment, the way a lead-lined case protects a radioactive source, designing electronics robust enough to survive dozens of close passes through one of the most hostile radiation environments in the solar system, while remaining sensitive enough to do precision science, was one of the defining engineering challenges of the mission. The spacecraft will reach Jupiter in April of 2030. It will not orbit Europa directly. The radiation environment in a close Europa orbit would destroy even the shielded electronics within months. Instead, Clipper will orbit Jupiter itself on a carefully designed trajectory that brings it into close proximity with Europa, approximately 50 times over the course of its primary mission. Each flyby will be brief, lasting only a few hours at closest approach, but each one will be precisely targeted, designed to scan a different region of Europa's surface and atmosphere with the full suite of instruments. 50 flybys, 9 instruments, years of data, and one question underlying all of it: is the ocean habitable, and is anything living in it? The 9 instruments on Europa Clipper represent the collective judgment of the planetary science community about the most important measurements that can be made from a flyby spacecraft without landing or drilling. Each one was chosen to answer a specific piece of the habitability puzzle. The magnetometer, called MAGIC, will measure the magnetic field around Europa with far greater precision than Galileo's instrument achieved. The goal is to directly confirm the ocean's existence and, more importantly, to characterize it. The induced magnetic field that the ocean generates carries information about its depth, its thickness, and its salt content. By measuring the field from multiple angles at multiple points in Europa's orbit, the team can construct a detailed picture of the ocean's geometry. How far below the ice does the ocean begin? How thick is it? How salty is it? These are the parameters that define the ocean's physical character. The ice-penetrating radar, called RESON, will send radio waves downward through Europa's ice shell and listen for the echoes. Different layers within the ice, including any liquid water pockets, will reflect the radio waves differently. The radar will map the three-dimensional structure of the ice shell in the way that ground-penetrating radar on Earth is used to find buried archaeological sites or underground voids. If the shallow liquid water pockets hypothesized to explain the double ridges exist, RESON should detect them. If the ice shell has internal layering consistent with convection, RESON should map it. If there are locations where the ocean comes particularly close to the surface, the radar will find them and mark them as priority targets for future missions. The thermal imager, called Themis, will map the surface temperature of Europa with enough resolution to identify warm spots, regions where heat from below is concentrated close enough to the surface to create a measurable temperature anomaly. Warm spots are places where tidal heating is locally elevated. They are the same places where the ice is thinnest, where the chaos terrain events are most likely to occur, where the chemical exchange between the ocean and the surface is most active. Themis will draw a heat map of Europa's surface that will tell mission planners and future mission designers exactly where to look. The spectrometers, including MISE and UVS, will map the surface chemistry at a resolution and sensitivity far beyond what Webb achieved from its enormous distance. Where Webb could identify the presence of carbon dioxide and sodium chloride in broad regions, Clipper's spectrometers will map those compounds at scales of miles rather than hundreds of miles. They will detect compounds too faint or too spatially concentrated for Webb to resolve. They will build a detailed chemical atlas of Europa's surface, identifying every major compound present and mapping where each one is most concentrated. The cameras, collectively called EIS, will photograph Europa's surface at resolutions high enough to resolve features tens of feet across. The chaos terrains, the double ridges, the lenticulae, everything that has been studied from Galileo's lower resolution images for the past 3 decades will be re-imaged in detail that transforms them from geological categories into individually mappable features. New chaos regions, new ridges, new warm spots will be discovered. The full complexity of Europa's surface will become visible for the first time. But the instrument that carries the most direct potential for addressing the life question is a mass spectrometer called MASSPEX, the mass spectrometer for planetary e-exploration. Europa has a very thin atmosphere, technically called an exosphere, produced when Jupiter's radiation kicks molecules off the surface and into space. This exosphere is extraordinarily tenuous, far too thin to be visible or to offer any protection from radiation. But it contains molecules that came from the surface, and through the surface, from the ocean below. MASSPEX will analyze those molecules during each flyby, identifying their chemical composition with extraordinary precision. The instrument can detect individual molecular species at concentrations of parts per trillion. It can distinguish between closely related molecules that differ only in the arrangement of their atoms. And critically, it can measure isotope ratios, including the ratio of carbon 1,2 to carbon 1,3 that Webb measured, but could not resolve in fine enough detail to draw conclusions about biological processing. If biological activity in Europa's ocean is producing organic molecules, and those molecules are finding their way to the surface through chaos terrain exchange and then being kicked into the exosphere by radiation, MASSPEX has a real chance of detecting them, not a guarantee. The concentrations might be too low, the biological signal might be masked by geological background, but the instrument's sensitivity is high enough that the possibility is genuine. What would a positive detection look like? It would not be dramatic. It would not be a message or a signal or anything that announces itself. It would be a pattern in the data. A mass spectrum showing peaks at molecular weights consistent with complex organic compounds, combined with isotope ratios that fall outside the range produced by known geological processes. A pattern that says the chemistry producing these molecules is not simple rock-water chemistry. It is something that preferentially selects the lighter carbon isotope, something that builds complex molecular architectures that geology alone does not typically construct, something that looks, in the careful language of chemistry, like it is being made by a process that runs on information, that something is life. A MASSPEX detection of this kind would not be proof. It would be the strongest evidence yet obtained for life beyond Earth. It would justify every subsequent mission. It would change the conversation permanently. The team has been scrupulously careful not to predict a positive result. The scientific standard for a claim of extraterrestrial life is appropriately very high. Alternative explanations would have to be exhaustively ruled out. Independent confirmation from other instruments would be required. The finding would have to survive years of scrutiny from researchers worldwide before any consensus could form. But the conversation is no longer about whether the question can be asked with scientific rigor. Europa Clipper makes the question askable. What comes back from MASSPEX over the years of its mission will either narrow the search dramatically or, in the most extraordinary possible outcome, end it. Europa Clipper is not alone in this investigation. While NASA was building Clipper, the European Space Agency was building its own Jupiter mission, with its own set of instruments, its own orbital strategy, and its own contribution to the question. The Jupiter Icy Moons Explorer, called JUICE, launched from the Guiana Space Center in French Guiana in April of 2023. Its primary destination is Ganymede, Jupiter's largest moon, which is also believed to harbor a subsurface ocean, though one buried far deeper beneath its icy surface than Europa's. JUICE will eventually enter orbit around Ganymede, the first spacecraft ever to orbit a moon of another planet other than Earth's own moon. But on its journey to Ganymede, JUICE will perform 2 close flybys of Europa, the first in July of 2031 and the second later in the same year. 2 flybys is not a lot compared to Clipper's 50. JUICE was not built to be an Europa specialist, but the value of JUICE's Europa observations lies not in their quantity, but in their independence. JUICE carries a different set of instruments, built by different teams, calibrated against different reference standards, operated by scientists who have approached the problem from their own angles. If JUICE detects the same chemical signatures at Europa that Clipper detects, the concordance between two independent instruments provides a level of scientific confidence that neither mission could achieve alone. Confirmation from a second, unrelated instrument suite is one of the strongest validations any scientific finding can receive. JUICE will also observe Europa from orbital geometries that Clipper's trajectory does not cover. Each flyby scans a slightly different portion of the surface and atmosphere. JUICE's flybys will add coverage of regions that Clipper may not visit, or may visit less thoroughly, providing additional pieces of the chemical and geological map. The two missions will overlap in time. Clipper will be deep into its flyby campaign at Jupiter when JUICE performs its Europa passes. The teams will be in contact. Findings from Clipper will inform what JUICE looks for. Anomalies detected by JUICE will trigger follow-up observations by Clipper. The two spacecraft will conduct, in effect, a coordinated investigation of the same world from two different vantage points, speaking to each other across the solar system through their data transmissions back to Earth. This level of international coordination around a single astrobiological target is unprecedented. It reflects a scientific consensus that the question Europa poses, whether life exists in its hidden ocean, is important enough to justify the resources of two major space agencies simultaneously. The answer, when it comes, will be the product of a collaboration that spans two continents, dozens of institutions, and thousands of individual careers. Central to everything Clipper and JUICE will be doing is a framework that astrobiologists call the ladder of life detection. It is worth understanding this framework carefully, because it shapes what the missions can realistically claim and what they cannot, and because understanding it is the difference between interpreting their results correctly and being misled by the inevitable complexity of the data. The ladder has several rungs, each representing a different level of evidence for life's presence. The lowest rung is the one we are already on: habitable conditions, liquid water, chemical energy, carbon, stable environment over geological time. This is what Webb has confirmed. It is necessary but not sufficient. A world can have all of these things and still be sterile. Mars once had liquid water on its surface. We have not found life on Mars. The next rung up is the detection of organic molecules. Organic chemistry is the chemistry of carbon compounds, specifically the complex chains and rings of carbon atoms bonded to hydrogen, oxygen, nitrogen, and other elements that form the building blocks of biology. Finding organic molecules on Europa would not prove life. Non-biological processes can produce organic chemistry. Meteorites contain amino acids. Comets carry complex organic compounds. The interstellar medium is full of organic molecules formed without any biological input. But finding specific classes of organic molecules, particularly those that biology preferentially produces over geology, would narrow the list of explanations significantly. MASSPEX is designed to detect organic molecules in Europa's exosphere. If it finds them, the finding lands on the second rung of the ladder. Important, suggestive, not conclusive. The rung above that is the detection of chemical disequilibrium. On Earth, the atmosphere contains both methane and oxygen. These two gases react with each other spontaneously. If life were not continuously replenishing the methane, it would disappear within decades. The simultaneous presence of both gases is evidence that something is actively maintaining a chemical system that would otherwise collapse toward equilibrium. Chemistry, left to itself, finds the lowest energy state and stays there. Life continuously pushes chemistry away from equilibrium, spending energy to maintain complex structures and gradients. Finding a chemical disequilibrium that cannot be explained by geology is one of the strongest indirect indicators of biological activity. In Europa's case, the relevant disequilibrium would involve the simultaneous presence of reduced and oxidized compounds in proportions that cannot be explained by simple rock-water chemistry. If MASSPEX finds both reduced organic compounds and oxidized species in the exosphere in patterns consistent with active biological metabolism, the disequilibrium signal would represent strong evidence for life. The rung above that is the direct detection of biosignatures, specific complex organic molecules that biology produces and that geology does not. Amino acids are a borderline case because some amino acids can form abiotically, but certain classes of lipids, certain specific molecular architectures, certain chiral preferences, the tendency of biology to preferentially produce left-handed rather than right-handed versions of the same molecule, would be very difficult to explain without biology. Chirality is worth a moment's attention. Most complex organic molecules can exist in two mirror image forms, like a left hand and a right hand. They are identical in composition but cannot be superimposed on each other. Chemistry without biological direction produces both forms in roughly equal amounts. Life, on Earth at least, uses almost exclusively the left-handed forms for amino acids and the right-handed forms for sugars. If mass specs detected amino acids in Europa's exosphere with a strong chiral preference for one form over the other, the signal would be extremely difficult to explain without invoking biological processing. Mass specs cannot detect chirality directly. Its design does not include that capability, but identifying the specific molecular classes present and comparing their isotope ratios to the ranges consistent with geological versus biological processing can still move a finding toward the higher rungs of the ladder. The highest rung, direct detection of cellular structures, genetic material, or anything that is unambiguously and exclusively biological, is not within reach of any current mission. Clipper is a flyby spacecraft. It samples the exosphere. It does not land. It does not drill. It does not return samples to Earth for analysis in terrestrial laboratories with the full array of instruments that biochemistry demands. That capability is a future mission, decades away, requiring technology that does not yet exist in flight-ready form. What Clipper can realistically achieve is a finding on the second or third rung of the ladder. Evidence of organic chemistry, possible evidence of chemical disequilibrium, a pattern in the data that either rules out biology at Europa or makes it the simplest explanation for what is observed. Either outcome is transformative. Ruling out biology at Europa, given everything Webb has confirmed about the ocean's habitability, would force a profound reassessment of what life actually requires. Finding evidence consistent with biology would justify the next mission and the one after that, and would begin the process of building toward a definitive answer that may take the remainder of this century to fully achieve. There is a scenario that no one in the community discusses enthusiastically, but that many scientists consider the most likely outcome of Clipper's mission. It is not the clean, positive result where mass specs returns data that clearly points to life. It is not the clean, negative result where the exosphere is chemically simple and biological signatures are absent. It is something in between. It is ambiguity. Complex organic molecules detected, but at concentrations that could be explained by non-biological processes if you work hard enough at the explanation. Isotope ratios that lean toward the biological range but do not fall clearly outside the geological range. Chemical disequilibrium hints that are suggestive but not definitive. A data set that the community spends years debating, with no clear consensus forming, with the most optimistic interpretation saying life is the simplest explanation and the most conservative interpretation saying we cannot rule out geology. This outcome is not a failure of the mission. Ambiguity in this context is scientifically real. The truth about Europa may be genuinely difficult to read from flybys of the exosphere. The signal from any biology that exists may be diluted by the enormous volume of the ocean, the 18 miles of ice, the thin exosphere, and the distance to Earth. A weak positive signal and the absence of a signal may be observationally indistinguishable at Clipper's sensitivity. If that is what Clipper returns, the community will have no choice but to call for a lander, a spacecraft that sits on Europa's surface, in the chaos terrain, and drills several feet into the ice, extracting material deposited recently from the ocean and analyzing it with instruments far more sensitive than anything a flyby spacecraft can carry. The Europa lander concept has been studied in detail, its science goals have been defined, its instrument payload has been proposed. It has not been funded. Funding a Europa lander would cost several $billion. It would take 15 to 20 years from approval to landing. The technology needed to survive Europa's radiation on the surface for even a few weeks would require development that has not yet been completed. The entire project is technically feasible but politically and financially contingent on the strength of the motivation to do it. That motivation depends on what Clipper finds. If Clipper returns ambiguous results, the scientific community will argue for the lander with whatever evidence it has. Whether the argument succeeds will depend in part on how the broader public and the relevant government decision-makers interpret the ambiguity. Whether suggestive but inconclusive evidence is treated as sufficient justification for an enormous investment is not purely a scientific question. It is also a question about how much humanity is willing to spend to answer whether we are alone. The horror of the ambiguous result is not scientific. It is psychological. It is the position of knowing enough to be almost certain but not enough to say so. Standing at the door of the most important discovery in human history and being told the door is not quite open yet, that you need another instrument, another mission, another decade, another few $billion before the answer becomes readable. That position may be where we end up. And if it is, the breathing wall of ice that Webb has been reading, the crystalline signatures and the carbon leakage and the salt deposits and the hydrogen peroxide at the wrong latitude, all of it will simply have to wait a little longer to tell its full story. But the waiting will not be passive. Every flyby of Clipper narrows the range of possible answers. Every dataset from JUICE adds independent constraint. Every laboratory experiment run on Earth to simulate Europa's chemistry refines the interpretation of what the spacecraft find. The answer is approaching. The question is only how far away it still is, and whether the instruments already in flight will bring it close enough to read. The ocean has been patient for 4 billion years. We have been patient for 40. The asymmetry in that comparison should tell us something about the appropriate pace of our expectations. We are not waiting too long. We are just beginning to look. Imagine a Tuesday morning, unremarkable in every outward sense. Coffee cooling on desks, emails accumulating in inboxes. Somewhere in a building at NASA's Jet Propulsion Laboratory in Pasadena, California, a small group of scientists is going through data from Europa Clipper's most recent flyby. The data has been sitting in the processing queue for 2 days. The preliminary analysis flagged something unusual in the mass specs readings, a cluster of molecular detections in a mass range consistent with complex organic compounds with isotope ratios that the automated pipeline marked for human review. The lead scientist opens the file. She looks at the spectrum. She looks at the isotope ratios. She pulls up the comparison database of known geological sources and runs the automated comparison. The geological models do not fit. She runs it again with different parameters. The fit does not improve. She calls a colleague. He looks at the same data. He is quiet for a moment. Then he says 4 words that will echo through the rest of both their lives. This does not look geological. What happens in the hours and days and months after that moment is a process of extraordinary scientific rigor. Independent teams reanalyze the data. Alternative explanations are proposed and tested. The instrument calibration is checked, then checked again. JUICE's upcoming flyby data is rushed through processing to see whether it shows anything consistent. Papers are written, reviewed, revised, submitted. The press office at NASA is notified with strict instructions to say nothing until the science is airtight. And eventually, after all of that, the answer that comes back from every check and every independent analysis and every alternative explanation that was tried and failed is the same. The chemistry in Europa's exosphere is not geological. The announcement, when it finally comes, will not look like a movie. There will be no single dramatic moment, no scientist running through a corridor with a printout, no president addressing the nation from an Oval Office. It will look like a press conference. Careful people in careful clothes, standing at careful podiums, using carefully qualified language to say the most unqualified thing that science has ever said. We have detected chemical signatures in the exosphere of Europa that are inconsistent with any known geological process and are most consistent with active biological metabolism in the subsurface ocean. That sentence or something like it, will be the most important sentence spoken by a human being in the history of the species. Not because of what it proves, because it will not, in that moment, prove anything definitively. It will not show a photograph of a cell. It will not display a strand of alien genetic material under a microscope. It will not introduce the first extraterrestrial organism to a waiting world. What it will do is shift the weight of evidence so decisively that the scientific community's working assumption about Europa changes from unknown to probably inhabited, and that shift from unknown to probably will change everything. Not slowly, not gradually, immediately. Within hours of the announcement, every major media organization on Earth will be running the story. Within days, leaders of every major nation will be expected to respond to it. Within weeks, religious institutions, philosophical traditions, educational systems, and political bodies will be grappling with what it means. The question that humanity has been asking since it first looked up at the night sky and wondered whether anything looked back. The question that underlies every ancient myth about gods and demons and visitors from above. The question that drives the search for extraterrestrial intelligence and has funded decades of radio telescope surveys listening for signals from distant stars. That question will have a partial answer for the first time in the history of conscious thought. We are not alone. The scientific implications will cascade outward for generations. The first and most immediate is statistical. If life arose independently in two places in the same solar system, two worlds that began from the same raw materials, the same stellar environment, the same initial chemical inventory, and that have never exchanged biological material in any known way, then the origin of life is not a singular accident. It is a repeatable outcome, a chemical process that runs to completion wherever the conditions are right. If that is true for the solar system, it must be true for the galaxy. The Milky Way contains between 200 and 400 billion stars. Conservative estimates suggest that at least half of them have planetary systems. Among those systems, tidal heating around giant planets produces ocean worlds on a regular basis. Europa is not exotic. It is representative of an entire class of object that almost certainly exists around countless other stars. If the conditions at Europa are sufficient to produce life, then life in the galaxy is not a rare exception. 11. From the feeble say, it is an expected outcome wherever the chemistry is favorable. The universe is not a sterile void with one inhabited island. The universe is a living system, distributed, mostly microbial, mostly hidden under ice, in places far from the warmth of stars, but alive. Alive in the deep cold, running on chemistry, in oceans sealed under ice around gas giants, scattered through hundreds of billions of star systems, present wherever tidal heating and liquid water and carbon have had sufficient time to run their experiments. This single revision to the picture of the cosmos, from one inhabited world to many, would be the most profound shift in humanity's understanding of its place in the universe since Copernicus removed Earth from the center of the solar system. And it would follow directly from a MassSpecs reading on a Tuesday morning in Pasadena. The implications for the search for intelligent life are equally dramatic, though in a more complicated direction. If microbial life is common, then the question of intelligent life becomes more pressing and more puzzling simultaneously. The Fermi paradox, the observation that a universe full of life should have produced detectable signals of intelligent civilizations by now, and yet we hear nothing, would become impossible to ignore. If life starts easily wherever the conditions are right, and if the galaxy is billions of years old, and if even a tiny fraction of life-bearing worlds eventually produces intelligence, then the silence of the cosmos would demand explanation. Either intelligence is extremely rare, even when life is common, requiring steps beyond chemistry that are not well understood, or intelligent civilizations tend to destroy themselves before becoming detectable. Or the distances involved are simply too large for any civilization at our level of technological development to bridge, or we are looking in the wrong way, or some combination of all of these. None of these possibilities is comfortable. Every one of them implies something sobering about the nature of intelligence, or the nature of the universe, or both. A confirmed detection of life on Europa would not answer the Fermi paradox. It would make the paradox impossible to set aside. The practical scientific response to a confirmed detection would be immediate and overwhelming. Every space agency with the capability to send a mission to Jupiter would begin planning one. The Europa lander, currently a concept in search of funding, would become the most urgent mission in the history of space exploration. The scientific goal of the lander would be specific and non-negotiable. Get to the surface of chaos terrain, drill into the ice, and extract material that has come from the ocean recently enough to carry intact biological signatures. Bring back what you find, not physically. The distance makes sample return impossible within any near-term time frame, but analyze it in place with instruments capable of imaging individual cells, sequencing whatever information-carrying molecules might be present, and determining whether Europa life shares any biochemical heritage with Earth life or represents a completely independent origin. That last question, whether Europa life is related to Earth life or truly independent, would be the defining scientific question of the following century. The solar system's history includes billions of years of meteorite impacts. Impacts eject material from planetary surfaces. Some of that material travels between worlds. Mars has delivered chunks of rock to Earth. Earth has almost certainly delivered material to Mars. Whether biological material can survive the journey, the vacuum, the radiation, the heat of ejection, the cold of space, the violence of landing, is not fully resolved, but some researchers believe it is possible. If it is, then life on Earth and life on Europa might share a common ancestor, exchanged billions of years ago in a meteoritic transfer that neither world recorded. If Europa life uses the same genetic code as Earth life, the same amino acids, the same molecular chirality, the shared ancestry hypothesis would gain enormous weight. If Europa life is biochemically alien, using different molecules, different coding systems, different fundamental chemistry, then life arose twice, completely independently, and the universe's capacity for biology is even greater than the most optimistic estimates have suggested. Either answer rewrites textbooks at a fundamental level. The field of biology, which has operated for its entire history on a sample size of 1, would suddenly have a second data point. And in science, the difference between a sample size of 1 and a sample size of 2 is not merely quantitative, it is qualitative. One instance proves that something happened. 2 instances begins to reveal the rules. But now hold the other possibility. Hold it carefully, because it is equally important and in some ways more demanding of our attention. Europa is dead. The missions complete their work. Clipper finishes its 50 flybys. JUICE adds its independent observations. A lander, funded in the optimism following Clipper's ambiguous preliminary results, reaches the surface of Terra Regio and drills several feet into the chaos ice. It analyzes the material directly, with the most sensitive instruments ever sent to another world. The data comes back clean. Organic molecules present, but only the simple ones that non-biological chemistry routinely produces. Isotope ratios fully consistent with geological processing. No chiral preferences. No molecular complexity beyond what rock-water chemistry can explain. No disequilibrium signatures. Nothing that requires biology as its explanation. Europa's ocean is chemically active. Europa's ocean contains carbon and salt and energy. Europa's ocean has been running its chemistry for 4 billion years, and nothing in that ocean has ever crossed the line from chemistry to biology. This result, the negative result, is in a specific and important sense the more frightening of the 2 possible answers. Think carefully about what it would mean. Here is a world with twice Earth's liquid water. Here is a world with confirmed carbon and confirmed energy and confirmed chemical richness. Here is a world where the conditions that researchers believe gave rise to life on Earth have existed, uninterrupted, for 4 billion years. Here is the same experiment that Earth ran, with the same ingredients, the same energy, the same time, the same darkness, at the bottom of a deep ocean near hot rock, and the experiment failed. No life, not even a trace of former life, not a fossil, not a remnant, not a chemical ghost of something that once lived and died. Nothing. The chemistry ran and ran and ran for 4 billion years and never once produced anything that could copy itself. If that is the answer, then our understanding of why life started on Earth is fundamentally incomplete. Something happened on Earth that did not happen on Europa, despite nearly identical conditions. Some factor, some ingredient, some event, some physical or chemical threshold was crossed on Earth and not on Europa. We do not know what it was. We thought we understood the conditions for life well enough that Europa should have it. We were wrong. The search for that missing factor would become one of the defining scientific projects of the following century. Was it a specific mineral chemistry at the seafloor? Was it the presence of a particular phosphorus compound? Was it the proximity of a tidal forcing at just the right frequency? Was it the availability of certain transition metal catalysts? Was it something about the ice shell's thickness, or the specific pH of the ocean, or the particular temperature gradient between the vents and the surrounding water? Was it something about the early solar system's delivery of specific organic precursors that Europa received in different proportions than Earth? Or was it something far more unsettling? Was it chance, a random molecular fluctuation that produced the first self-replicating molecule on Earth through sheer statistical luck, and that simply has not yet happened on Europa, despite 4 billion years of trying, not because the conditions are wrong, because the probability is very low and the lottery has not yet paid out. If the origin of life is a genuinely low probability event, then Earth may be extraordinary not because of its conditions but because of its luck. And if that is true, then intelligent life, which requires not only the origin of life but billions of years of subsequent evolution, an extinction event at the right time, the development of multicellularity, the emergence of nervous systems, the particular cognitive leap that produces abstract thought, is vanishingly rare, perhaps unique. Perhaps we are, in all the observable universe, the only minds that have ever turned and looked at the cosmos and wondered what it was. That possibility should not produce arrogance. It should produce something closer to vertigo. The responsibility of being the only conscious witness to an unconscious universe is not a comfortable thing to contemplate. It means everything that has ever been thought, felt, created, discovered, loved, and mourned in the entire history of consciousness has happened in one small corner of one ordinary galaxy, on one small planet, in one thin sliver of geological time, a single candle in a darkness so vast that even light has not had time to cross it. The empty Europa is in some ways the lonelier answer, not merely because we would be alone, though we would be, but because we would be alone in a universe that has had every opportunity to produce company and has not done so. The universe is not cruel. It is simply indifferent. It does not withhold life out of malice. It simply runs its chemistry and produces what the chemistry produces. And if the chemistry of an ocean world as favorable as Europa produces nothing, then the chemistry of the universe may produce minds only very rarely, if ever again. There is a third possibility that sits between the clean positive and the clean negative, and it is the one that many researchers, speaking carefully and off the record, consider most likely for the next decade or two. Not confirmation, not absence, évidence. Evidence that is real but insufficient. A mass-specs detection that is genuinely anomalous, genuinely difficult to explain geologically, genuinely consistent with biological processing, but that falls short of the standard required for scientific consensus on the most extraordinary claim in the history of science. A dataset that the most optimistic interpretation reads as strong evidence for life, and the most conservative interpretation reads as a possible but unconfirmed anomaly requiring further investigation. This is not a failure. It is the normal process of science at the frontier of the unknown. The discovery of the cosmic microwave background radiation was an anomaly before it was understood. The first detections of gravitational waves were treated with extreme skepticism before they were confirmed by repeated observation. The first evidence for dark matter was debated for decades before it became a standard part of cosmological models. Science does not jump to extraordinary conclusions from single datasets, however compelling those datasets appear. A partial positive result from Clipper would be the beginning of a process, not the end of one. It would justify the lander. It would justify the sample analysis mission that follows the lander. It would justify the decades of follow-up work that would gradually, carefully, rigorously build the case from suggestive to probable to confirmed. This process might take 50 years from the first anomalous mass specs reading to a result that the full scientific community accepts as definitive. 50 years is a long time by human standards. It is nothing by cosmic standards. It is nothing compared to the 4 billion years the ocean has been running its experiment in the dark. The horror of this scenario, if horror is the right word, is not scientific. The science is proceeding exactly as it should. The horror is existential. It is the position of being close enough to the answer to feel its shape, but not close enough to hold it. Of knowing that the most important truth the universe has to offer is visible through the data, somewhere, but that the resolution of the instruments and the statistical constraints of the observations and the appropriate demands of scientific rigor stand between us and the moment of knowing. It is the horror of being almost certain and having no right to say so. Whatever the answer turns out to be, the act of asking the question with sufficient rigor to get an answer is itself one of the most remarkable things that has ever happened on the surface of a planet. Consider the full chain of events that produced the moment when MassSpec's data is opened on a Tuesday morning in Pasadena. A species evolved on a small rocky world around an ordinary star. That species developed language, then writing, then mathematics, then the scientific method, then the telescope, then the rocket, then the computer, then the precision engineering needed to build instruments sensitive enough to detect individual molecules in the exosphere of a moon 400 million miles away. All of this in roughly 10,000 years of civilization, a period so short on cosmic timescales that it does not register as a rounding error in the age of the universe. And with those tools, built in that eye blink of time, the species asked one of the oldest questions its consciousness had ever generated. Is there anyone else? And sent a machine the size of a basketball court, powered by the physics of the sun, guided by the mathematics of celestial mechanics, carrying instruments built on the quantum mechanical principles of molecular spectroscopy, yen to a moon it had first seen through a glass lens 400 years ago, to try to read the chemistry of an ocean no eye had ever seen. This is extraordinary, not because of what it might find, because of what it represents about the nature of the species doing the finding. A being small enough to hold in your arms, brief enough to live and die in a single century, fragile enough to be ended by a virus or a vehicle or a single missed heartbeat, capable of spanning 400 million miles, with its curiosity and asking a question that the universe itself cannot hear. Whatever Europa is, the act of going there to ask is already one of the most improbable and most beautiful things that has ever happened in this region of the galaxy. The answer, when it comes, will only be the second most remarkable thing. Come back to the beginning. Come back to the moment before any of this was known. A telescope floating 1 million miles from Earth tilts its golden mirrors toward a small frozen moon. The command to observe has been transmitted. The mirrors adjust. The detectors open. For a few minutes, the most sensitive infrared instrument ever built stares at a world that most people on Earth have never thought about. A world smaller than our own moon, orbiting a gas giant in the cold dark beyond the asteroid belt, covered in cracked ice, bathed in radiation, lit only by a sun so distant it appears as little more than a very bright star. The data begins to arrive. At first it looks like noise. It always looks like noise. The photons arrive one at a time, each one carrying a tiny fragment of information about the surface below. The detectors count them. The processing algorithms sort them. Gradually, over minutes that feel much longer to the people watching the screens, a picture assembles itself from the individual photons the way a mosaic assembles itself from individual tiles. Not a photograph, a spectrum. A record of which wavelengths of infrared light bounce back from Europa's surface, and which were absorbed by whatever molecules were sitting on that ice. The spectrum sharpens. The signal rises above the noise, and there, in the infrared fingerprint of a frozen moon 400 million miles away, a pattern appears that should not be there. Carbon, rising from a hidden ocean. concentrated in the most broken, most recently disrupted, most geologically active region on the visible face of the world, sitting next to salt from a deep salty sea, accompanied by hydrogen peroxide in exactly the wrong latitude, preserved in crystalline ice that should have been radiation damaged into disorder long ago. The room goes quiet, not because anyone is afraid, not because the data is ambiguous, because the data is clear and the clarity is enormous, and the enormity of what the clarity implies takes a moment to settle in the way that genuinely large things always require a moment before they can be fully held. Something is down there. Let us hold what we now know, not what we suspect, not what the models suggest, what the observations have directly confirmed. Europa has an ocean. The magnetic measurements from Galileo established this beyond reasonable doubt 3 decades ago, and everything since has deepened the confirmation. Liquid water, salty, electrically conductive, sitting beneath 18 miles of ice, wrapping the entire moon in a single continuous body of water with a volume roughly 9 times greater than all of Earth's oceans combined. That ocean contains carbon. Webb confirmed this directly. The carbon dioxide on the surface of Terra Regio has an isotope ratio consistent with an internal source, a geological source, the kind of source that speaks of billions of years of rock-water chemistry running at depth. It was delivered to the surface recently, meaning within the last few million years, meaning the process that delivered it is ongoing. The ocean is not chemically inert. It is actively producing and transporting carbon compounds. That ocean contains salt, sodium chloride, the same mineral that makes Earth's seas salty, concentrated in the same chaos region as the carbon, in the same pattern, with the same freshness. Both chemicals sitting together on a broken, icy surface that looks exactly like what you would expect from a region where the ocean below has been pushing its chemistry upward through the ice above. Repeatedly, over geological time, the surface is producing oxidants, hydrogen peroxide, concentrated at the equator where carbon dioxide from the ocean catalyzes its production, providing a potential energy source that could, through the slow conveyor belt of the convecting ice shell, be delivered downward into the ocean over millions of years. The ocean is not cut off from chemical energy from above. The ice is breathing it downward. The ice itself is not a sealed wall. It is a porous, fractured, internally active material full of microstructure, riddled with stress features, bearing the geological signatures of chaos events that have repeatedly connected the ocean below to the surface above, leaving behind the freshest crystalline ice that should not exist alongside amorphous ice that has had time to be radiation damaged. 2 signatures that together say the same thing in different chemical languages. The surface is being refreshed, the interior is active, the exchange is ongoing. Every piece of evidence points in the same direction, not toward life, toward the conditions that make life possible, toward the chemistry that makes life probable, toward a world that has had everything the recipe calls for, sitting undisturbed, running its experiment in the dark, for a span of time that makes the entire history of human civilization seem like a single afternoon. There is something that does not get discussed often enough in the scientific literature, something that tends to appear only in the quieter moments of conversations between researchers who have spent years thinking about this world. It is a thought that is not quite scientific and not quite philosophical, but sits somewhere between the two, in the space where data ends and meaning begins. Europa does not know we are looking. Whatever is happening in that ocean, whatever chemistry is running in the dark water around the possible vents on the possible seafloor, whatever has been produced by 4 billion years of molecular experiment in a sealed environment, none of it has any awareness of the mirrors that turned toward it in 2022. None of it registered the photons that bounced off its surface and traveled 400 million miles to a detector floating in space. None of it knows that on a small rocky world in the inner solar system, beings made of the same carbon and water and salt that leak upward through its ice spent decades designing instruments specifically to read its chemistry. None of it knows it is being studied. The asymmetry of that situation is one of the strangest things about the moment we are in. We know about Europa. Europa does not know about us. We have been watching it for 4 centuries, since Galileo Galilei first turned a crude telescope toward Jupiter on the 7th of January, 1610, and saw 4 points of light arranged in a line beside the planet. He did not know what they were. He watched them over the following nights and realized they were moving with Jupiter, orbiting it. He had discovered that not everything in the cosmos orbited Earth. He had made the crack in the old picture that Copernicus had started, and that would eventually widen into an entirely new understanding of humanity's place in the cosmos. One of those 4 points of light was Europa, the same world, the same ocean, the same chemistry, sitting there in 1610, exactly as it sits now, sealed and silent and full of whatever it is full of, while a man in Padua squinted through a tube of glass and could not have imagined what he was looking at. 400 years passed. The tube of glass became the James Webb Space Telescope. The man in Padua became thousands of scientists across dozens of countries with computers and orbital mechanics and infrared spectroscopy and decades of collective understanding of planetary chemistry. And in all that time, from 1610 to 2022, Europa's ocean continued doing exactly what it was doing when nobody was watching, running its chemistry, cycling its minerals, breathing its gases slowly through the ice, indifferent to observation, because indifference requires awareness, and the ocean has none. But we do. We have awareness. We have curiosity. We have the particular gift and burden of consciousness that makes it impossible to look at a world like Europa without wanting to know what is in it. We cannot look at a locked door without wanting to open it. We cannot find chemistry that looks like the preconditions for life without asking whether life is there. We cannot be told that an ocean larger than all of Earth's seas has been sitting in the dark for 4 billion years without wondering whether anything in that ocean has ever moved, grown, divided, adapted, and survived. That wondering is not a weakness. It is the defining characteristic of the thing that we are. In the years ahead, the data will continue to arrive. Europa Clipper will begin its flyby campaign in 2030 and will spend years building a detailed picture of the moon that makes everything we currently know look like a sketch. JUICE will add its independent observations. Future telescopes may improve on Webb's chemical readings. Laboratory experiments on Earth will continue to refine our understanding of what the chemistry on Europa's surface means and where it comes from. The models will improve, the uncertainties will narrow, the picture will sharpen. And at some point, on some unremarkable morning or afternoon in some laboratory or control room somewhere on Earth, the data will say something definitive. Either the chemistry is biological or it is not. Either the experiment ran to completion in that ocean, or it is still running and has not produced life yet, or never will. We do not know which answer is waiting. We do not know when it will arrive. We do not know whether it will come from Clipper's mass-specs readings, or from a lander drilling into chaos terrain, or from some instrument we have not yet designed in a mission we have not yet funded, launched toward a world that has been waiting for a visitor for 4.5 billion years. What we know is that the answer exists. It is there, in the ocean, in the chemistry of the water, in the isotope ratios of the carbon compounds, in the presence or absence of molecules that only biology constructs. The answer has been sitting there since before the first cell appeared on Earth, before the first fish swam in an ocean, before the first creature lifted its eyes from the water and looked at the sky, before the first human pointed at Jupiter and gave it a name. The answer has been patient. We are finally becoming capable of reading it. Think about what that means for a moment. Not scientifically, not analytically, just as a fact about the situation you are in right now. You are alive at the specific moment in the 4.5 billion year history of Europa, when humanity has developed precisely the instruments needed to begin reading the chemistry of its hidden ocean. Not a century too early, when the telescope technology was insufficient. Not a century too late, when the answer is already established history. Now, this decade, this generation, the James Webb Space Telescope exists now. Europa Clipper is in flight now. The data is arriving now. The conversation that has been building since Galileo squinted through his glass in 1610 is approaching. Now, the moment when it produces something other than speculation. You are living at the hinge point of that story. That is not a small thing to be. Most generations of humans who ever lived and wondered about the night sky had no means of doing anything about their wandering beyond mythology and philosophy and the patient accumulation of observational data that moved the understanding forward by degrees across centuries. They looked up. They did not know. They passed their wondering to the next generation, who passed it to the next, who passed it to the next, across all of recorded history, until the wondering accumulated enough momentum and enough technological foundation to produce a spacecraft that can answer what all of those generations were asking. You are the generation that gets to find out. Whatever the answer is, that position is remarkable. The wondering is yours to complete. The instruments are flying. The ocean is being read. The chemistry is speaking its slow, patient language into detectors sensitive enough to hear it across 400 million miles of empty space. On the surface of Europa, right now, the ice is doing what it has always done, cracking along the ridgelines, shifting in the chaos terrains, absorbing Jupiter's radiation and converting it into chemistry, exhaling carbon dioxide and salt upward through the fractures in the shell toward a surface that no atmosphere warms and no wind crosses and no foot has ever touched. The ice does not know it is being watched. 60 miles below, if the models are right, the ocean is doing what it has always done, circulating slowly in the dark, carrying its dissolved minerals through pressures that would crush anything a human engineer has ever built, receiving heat from the rocky seafloor below and cold from the ice above, and finding its chemical equilibrium somewhere in the water column between, running whatever reactions the chemistry of a salty, carbon-bearing, tidally heated ocean runs when left alone for 4 billion years with no observer and no interruption. The ocean does not know it is being studied, and in between, the ice is breathing, slowly, imperceptibly, on timescales that make a human lifetime look instantaneous. Carbon rising, salt rising, oxidants sinking, crystal structure forming and being destroyed and forming again. The slow geological conversation between the surface and the deep carrying fragments of the ocean story upward to where light can read it. The conversation has been going on since before the Earth had continents. It has been going on since before the atmosphere had oxygen. It has been going on since before any eye existed anywhere in the solar system to watch it. It will continue going on regardless of what we find or do not find, regardless of whether any answer ever reaches us, regardless of whether the species doing the looking survives long enough to understand what it is looking at. But we are looking, that matters. That is the extraordinary thing. In a universe that does not look at itself, a small arrangement of carbon and water and salt on a rocky world around an ordinary star has developed the capacity to turn its instruments toward another arrangement of carbon and water and salt on an icy moon around the largest planet in the system and ask whether the two arrangements have anything in common. Whether the answer is yes or no, the asking is already one of the most improbable events in the 4 billion year history of this solar system. A hidden ocean, sealed in darkness since before the first cell appeared on Earth. A species, brief and fragile, and curious beyond all reasonable expectation, pointing its best instruments at the ice above it and listening for what leaks through. The ice breathes. The data arrives. The answer waits. It will not wait forever. Neither will we.